What's up, everyone? This is Ben, and we are doing 10 free response questions for the AP Calculus ABBC exam. And this is day 3. All right. Day 4, I just want to point out that I did have a few updates, but the time for tomorrow, I am going to do the review at 3:30 p.m. Eastern Time. Okay. If anything changes, I will let you know, but that is the time I plan on doing. I'm glad I could just get this done a little bit earlier in the day because going till midnight, I don't think is really a good idea when you have to be up and take the test at 8 a.m. Unless you're on the West Coast, then you get that 3 hour, you know, time difference there. So that's, yeah, just pointing that out. So, all right, let's get rolling here. So the questions I have linked in the description. So if you want to follow along, but I also put the year at the top so you could see. I try to go back pretty far so that chances are maybe you didn't do those questions. But even if you did, I would say it's still helpful to hear another person talk about them. But wow, 37 of you already here. This is like pretty awesome. So thank you all for being a part of this. I really can't say it enough. Like, just thank you. It's really exciting to see like how many people that this is reaching around this time of year, and I'm just grateful that you all chose me. I'm at Dogman. Yeah, I'm glad that the videos helped, but awesome work to you too for going on YouTube and try to step your game up. Um, so DY gonna be harder this year. Yeah, I mean I would have to see. IVT MVT is going to be part of the stream for sure. So I will talk about those two. And all right, yeah, I say let's just get rolling here. And please, I'm glad people are lighting up the chat, bringing this live stream to life. The only guidelines I say is just being respectful to each other in the chat is all I will ask. All right, but let's get rolling here. So first one, 2002 Calc AB, but this is also on the BC exam, rate and accumulation. And for a question like this, we should be thinking rate in, rate out. Okay, so rate in, rate out is a popular type of question. So when I'm doing these, I'm just thinking like, okay, it's rate in and rate out. That's what I'm on the lookout for. So here, just looking at what they gave us, we're talking about an amusement park. So the rate at which people enter the park. So this represents the rate in. And the next one here, the rate at which people leave the amusement park is the rate out. Okay, so this is just something I'm on the lookout for when I'm doing questions like this. All right, now this is a calculator question. So the first thing I like to do, because at some point we're going to have to integrate this, is I like to switch over to the calculator view. I'm going to go to the y equals. And in the y1 spot, I have the questions also on paper, so I can refer to, but I'm just going to hit alpha y equals enter to pull up a fraction. And I'm going to write in the function for the rate in, E of t. It's 15,600. And then we have t squared, but we'll use x. And we have minus 24x. And then plus 160. Okay, so that's our rate in function. And for the rate out, it's another fraction here. So we have 9890. And our denominator is, I don't need to put this in parentheses, but I'm just copying it exactly as it appears. Now, I would say please make sure that you type carefully. Now, you'll be anxious on test day. If there's anything I would be worried about, would be making a typo. So just, try not to make a typo if you could help it. If you do, though, but you get the concept, it's usually, yeah, just 1 point for the correct answer itself. Like, they understand typos are very possible. All right, so now I'm going to scroll down a little bit and we'll start answering this. So part A is how many people have entered the park by 5 p.m. And one thing to point out here, if we take a moment to read through this, E and L are measured in people per hour. So these are the units for the question. And T is measured in hours after midnight. Okay, so this is also important here. And these functions are valid. So this is very big too for this domain here from 9 to 23. And at time t equals 9, also important stuff, is at t equals 9, there are no people in the park. Okay, so that's just some important stuff that we want to pay close attention to detail with later. So when they ask us how many people have entered the park by 5 p.m., we don't actually have to worry here and do any like third grade math when we're like adding hours, to when is this? Oh, after midnight, like doing midnight plus, how many hours gets me to 5 p.m. We don't have to worry about that. They're telling us, hey, t equals 17. So here we're going to do the integral of, and we have 9 to 17. Now, if you say 0, the trap here is saying 0, that the hours of operation are from 9 to 23. The park is not open at midnight, okay? The park opens, if we just follow this line of reasoning, at 9 a.m., okay? So from 9 to 23, but they're saying how many people have entered the park by this time. Now, enter the park is going to be related to the rate in, okay? So entered the park is talking about the rate in. So we're going to integrate E of t. This is the calculator section, so we're not going to do this by hand. Now, the concept, this is just the concept that I want people to get. Like, why do we integrate? Because some people just like follow the technique and just hope for the best. So why we integrate is that E of t and L of t, the units are people per hour. Okay, so if I derive, I go forward this way. So the derivative of E of t would be E prime of t, and it would be people per hour squared. So it's people per hour squared, and then before that would be people. So if deriving sends us this way, and we want to go backwards, we would anti-derive E of t to get here. Okay, another way to see this, the concept, is that it's people per hour, and dt is hours. Okay, a small change in the time, and the units cancel, giving you people. All right, so I want people to understand why we integrate. So that's just hopefully, helping you out. But otherwise, honestly, for this, you're just going to go to the calculator and you're going to write in. So we're going to hit on the main screen, math 9, and we're going from 9 to 17. And the function E of t is in the y1 spot. So I can press alpha trace y1. That way I don't have to rewrite it all over again. And then we have 6004. Okay, so this one is, they're going to give us 6004. All right, let me just see. Let's crop this. And yeah, I switched programs. The first 2 days I was using, what was it, Notability, but the pen was lagging terribly. So I'm going to go back to GoodNotes. All right, so this is 6004 because they said round your answer to the nearest whole number. So 6004 people. Okay, cool. All right, now part B, we're moving on. We have, let's see here. Actually, you know what? I'll do the colors later on. So, all right. So part B, the price of admission to the park is $15 until 5 p.m. And then after 5 p.m., the price of admission to the park is $11. So how many dollars are collected from admissions to the park on a given day, and round to the nearest whole number? So for this one, you see how we went from 9 to 17. And this told us how many people entered the park at this time. So what we could do is the price of admission until 5 p.m. is $15. So if we multiply this by 15, the number of people that enter the park from this time by 15, that tells us how much money the park people make. But then they said after 5 p.m. So for the remaining hours here, now we're going from 17 to 23 when the park closes. Okay, remember the hours of operation are from 9 to 17. So I'm sorry, or from 9 to 23. So if we go from 9 to 17, we still have to go from 17 to 23 here. And we're still integrating E of t because it's based on how many people enter the park. Okay, those, like every time someone enters the park, they got to pay for their tickets. And the price of admission after that time is 11. So now it's the same idea. We're just going to go over to the calculator. So let me just open this up. And this time around, we've got 15, math 9, and we're going 9 to 17. And we've got alpha trace, and then plus 11 times math 9. And we're going 17 to the part closes at 23. So these are going to be the values here. And now we get our total, and it's going to be 104,048. Okay, they said to the nearest whole number here. So we're going to round this to, I'll just cover that up. That for part B, we're rounding to 104,048. All right, so here we are. 90, so just reading the chat here, a 90 out of 108, that's really good. That's like a super 5. Yeah, because you need like in the 70s-ish, depending on where they draw the 5 mark. But a 90 is like a pretty safe bet. So very nice work there. How do you store a value? So at Xenon, always label your units. Yeah, so here, if they tell you indicate units of measure, then I would 100% write the units. Like, I mean, it doesn't hurt here to say like how many people, this many people. Okay. How many dollars are collected? You know, if like you want to put a dollar sign here, will it erase the whole thing? It will. All right, I'll just write it again. But the word to look out for is indicate units of measure, because if they don't say indicate units of measure, that means that they're not going to be counting that as part of scoring criteria. Okay, there are going to be questions later. If I take a look here, indicate there, I have to. Oh yeah, there is going to be a question later that says indicate units of measure. So the rubric is very precise. Just so you know, the point spread here, this one is worth 3, this is worth 1, this is worth 3, and this is worth 2. Okay, that's the point spread for this question. All right, so now we'll come back. Part C is worth 3 points. There's a lot to do here. And I find what's nice here, though, is that they defined h of t for us. They created a function for us that tells us how many people are in the park at any given time during the hours of operation. So they tell us the value h of 17 to the nearest whole number is 3725. And then they want us to find the value of h prime 17 and explain the meaning of both in the context of the amusement park. So here, if they're defining h of t to be this function here, the formula that we're going to need here is that the derivative of an area function like this. So the fundamental theorem of calculus tells us this is f of x. So I'm going to use that concept here and say that h prime of t is equal to e of t minus L of t. Okay, so that's the values here. So this is the rate in minus the rate out. So then if we think about what does this actually mean? Well, for one, let's find h prime of 17 first. So for this one, all we got to do, rate in is in the y1 spot. So I have y1 at 17. I just put parentheses 17 and close it. Minus alpha trace y2 is my rate out. I put a parenthesis, a 17, and I close it. And, all right, hang on. If your calculator's in fraction mode, switch it to decimal. So if you borrow a calculator from the school, it might be reset. So here, this is better. All right, and this is what we're going to use to answer the question. And let me just shrink this down a little bit. Okay. So now this, we're going to find h prime of 17. H prime of 17 is equal to negative 380 and then 0.281. And the units here, we're going to tie in a moment. So h, we have to just think very carefully about this. This is the rate in minus the rate out. When we integrate the rate in minus the rate out, that's telling us how many people are in the park. Okay, so this is going to tell us, let me just make that neater, how many people are in the park. okay, at any given time. They told us there were no people in the park when the park opened. So here, h of 17 represents the number of people in the park at t equals 17. They told us t equals 17 is 5 p.m. So if we really want to get precise, we could say 5 p.m. But h of 17, so h of 17 is the number of people in the park. Oh no, is this program doing the same thing that the last one did? So h of 17 is the number of people. This is definitely better than yesterday's program, though. At t equals 17. Okay, so that's for that part. And then h prime of 17 is the rate of change of the number of people at the park. So here, this is saying here, like if you think about it, once again, this is rate in and rate out. So if the rate in minus the rate out at a certain time is negative, that means that people are leaving the park faster than they're entering the park. So the number of people at the park is decreasing at roughly 380 people per hour. Now, I'm saying people per hour because t is measured in hours after midnight. Okay, and L of t, E of t, and L of t are measured in, well, they tell us even here, E of t and L of t are measured in people per hour. So that's just how this is all tying in. So I would say here, in the context of the question, if we write it out, that at t equals 17, people are leaving the park at a rate of roughly, I'll just round it, 380 people per hour. Okay, so that's that. Cool. Yeah, that one, there was a little bit to do. Not the worst question. All right, so now we got this. Just group all of this together. And all right, just so I could fit the last part here. Okay, so that's, here we go. Yeah, sorry, I gotta do a little surgery on this. Resize. Okay, cool. So part D, at what time t from 9 to 23 does the model predict that the number of people in the park is a maximum? So here, for part D, if h is the number of people in the park at any given time, then h prime of t, we're going to set h prime of t equal to 0. Okay, because once again, if h is the number of people in the park, we're going to set h prime equal to 0 to see where the critical points are. Because what I'm imagining here is we have like some graph of h. So h, and then whatever this thing looks like, the maximum is going to occur where the slope is equal to 0. So that's why we're setting h prime equal to 0. And we're going to do this in the calculator. So now we go over to the calculator. We go to the y equals, and we're doing the rate in minus the rate out. So I'm going to do alpha trace y1 minus alpha trace y2. Learning these shortcuts is so helpful because you don't want to spend all your time typing. That's going to eat up a lot of time. So yeah, make sure that you're able to do stuff like this. And now here we are on the interval from 9 to 23. So when I go to the window, I'm going from 9 to 23, and I'm looking for a sign change. So there it is. There's our sign change. Second trace 0, and let's find it. Okay, there it was. Enter once, go to the right, enter again. So there's our 0. I'm going to press second mode, second minus sign for the answer. And someone asked, how do I store? I could just press store alpha math. And then now I could store it as the letter A. And what we're going to do is we're going to integrate. We're going to find at what time t does the model predict that we have a maximum? Okay, so let me just bump this up a little bit. At what time t does the model predict that the number of people in the park is at a maximum? So you see how the function is e of x minus L of x, the integral from 9 to t. So that means here that we're integrating y4. That's rate in minus rate out. So I have math 9. Integral from 9 to 9 is just 0. So first I'll find what is the integral from 9 to a of our rate in minus rate out. And the rate in minus rate out I saved in the y4 spot. And I just press enter. Okay, and I'm getting this value here. And then I do this one more time, but the end of the interval is at 23. So 23, and then enter. So these are the two values that I'm going to need. Okay, so we have this. All right, and now we could write out our solution. So for the rest of this question, now all I have to say is that I have t h of t, and this is true at time equals 15.7981471. Okay, I'll call this t1 so that I don't ever have to write that number again. All right, and not 0. We plugged in the endpoints were 9 and 23. Okay, so 9 and 23. Well, at the beginning of the day, there were no people in the park. At T1, when we plugged in this time, we had 3950. And then we have point, let's just see, did they tell us? They're just asking us at what time T. So here, I'll write out some significant digits here. I'm going to write out 680. And then at 23, it was 1.014. Okay, which makes sense. At the end, people are leaving the park. So like that last person is just lagging behind. I hope they're okay. So now here, they're saying justify your answer. Right? Or they didn't even say justify, but at what time t does the model predict? This would count as justification. So we would just say here, the number of people is maximum at t equals this. Okay, so the number of people. So the number. Oh no, the pen is becoming less responsive. Okay, and then 15.7. I can even say 798 here because you could round to 3 places. All right, so there's one time. So you could round the time. I don't round if I'm looking for the y value, because if you just always round to 3 places the whole question, then yeah, I check the endpoints. Yeah, I would. Technically though, like if you want to write a fancier argument, if you only have one critical point, and at the critical point, there's a sign change from positive to negative, not only is that a local maximum, it's the absolute maximum, because that's the only time the sign changes on the interval, okay? Oh, for part C, would you define H prime as the rate of which people in the park is, since this one is the number of people in the park decreasing? Yeah, because since the rate came out negative, that's why I said at t equals 17, people are leaving the park at a rate of roughly. Okay, because if the rate was negative, that means H is decreasing, and that's the number of people. And decreasing the number of people means they're leaving at a rate of. Okay, or you could even say the number of people in the park is decreasing at a rate of. So, yeah, that's, there's a lot of ways you could explain that to get full credit. It's not just, don't just think there's one way to get the full credit. All right, so another Calc AB question. The BC questions are going to be the last 4. All right, so this one, let's just see here. We get a calculator, we have velocity, and we want to know the acceleration at 4. So here, if we just want to find the acceleration, let me just see the point spread here. This is 1, 3, 3, 2. Okay, so part A is just like a matter of you knowing how to type in the calculator. So here I would go over to the y equals, clear out all this stuff. And I could find this by hand, but remember, if you're in the calculator section, unless they're asking you for like the derivative of x, you know, you might as well just type stuff in the calculator and not worry too much. So first, they want us to find the acceleration at 4. So acceleration is the derivative of velocity. So I take my velocity function, which I saved in y1, and I plug in 4 to its derivative. Okay, so I'm deriving our velocity function, and I'm plugging in. And you see here, this works out to, I'll just drag it out like this so we can see. All right, so this is going to work out to, I'll just write it over here. Part A of, well, you know, I'll even say it like this. How about V prime of 4? Just to show like, hey, I took a derivative. And they know in this section here that you're using the calculator. So it's negative 0.524 if we round. Okay. They didn't say units, and they didn't give us units here. So that's what's like annoying. Sometimes like a physics question, should have units, but yeah, just do what they tell us to do. All right, part B, we want to know, we have 2 statements. So for 3 to 5, the velocity of the object is decreasing. Statement 2, for 3 to 5, the speed of the object is decreasing. So for this, all we have to do is we could just make a sign chart, and we're looking here from 3 to 4.5. Okay, so I'm looking here from 3 to 4.5. But now let's pretend I don't know the chain rule. I'm going to find my acceleration by deriving my velocity function, and I'm too lazy to type this over, so I'm going to press alpha trace y1 and derivative with respect to x. And now window, we're going from, let's just see here, 3 to 4.5. Okay, and we're just looking to see if it's positive or negative, our graphs. All right, and let me actually shrink this down a bit. Let me go -5 to 5 so we could get a better view. I didn't bring my reading glass. Okay. So what do you notice here? From 3 to 4.5, the blue was velocity, red is acceleration, but velocity and acceleration are both negative from 3 to 4.5. You might say like, wait a minute, what about the endpoints? So if I go second window and switch it to ask, and I go to my table at 3 and at 4.5, okay, I get a 0 here and a 0 here. So it's really just the endpoints that are 0. The left endpoint is 0 at the blue, and the right endpoint is 0 at the red. But we could say strictly between 3 and 4.5, negative. Okay, so here, if I just make a sign chart, I say V, and let me just mark this up here. From 3 to 4.5 is negative, and acceleration from 3 to 4.5 is also negative. All right, maybe I'll call this V of t so that it matches the question, and I'll call this A of t. Oh no, this marker is also possessed like yesterday or 2 days ago. Okay, now the argument here, I'm going to say 2 things. Statement 1, the velocity of the object is decreasing. That is true because acceleration is negative. Okay, if you want to see if your velocity is decreasing is true when the derivative of velocity is less than 0. Okay, so if the derivative of velocity is less than 0, then this means velocity is decreasing. Okay, so this is decreasing. I want to point, let me just see something here. That's recognized shape, picture. Yeah, I'm just seeing, maybe it's just a little bit of lag here. Doesn't it ask for speed and velocity not? Okay, so I'm going to get to that in a moment. But if you want to show something is speeding up, if velocity and acceleration have the same sign, the speed is increasing. If velocity and acceleration have different signs, speed is decreasing. Okay, I'll show another way to do this also, but that's the idea. Alrighty. So for this one, now all I have to do is say statement 1. So statement 1 is consider, are these statements correct? So I'll write our answer over here. So for statement 1, let me write it like this. I'll just say statement 1. Yeah, this is going to annoy me. Statement 1 is correct. And now because A of t is less than 0, on 3, 4.5. Okay. So next one, statement 2 is correct. A is also correct. Because so V of t is less than 0. Yeah, this is going to drive me nuts. I might have to switch over to notability in a moment, because this is like becoming worse than notability. Okay, on. Okay. And if you think about this conceptually, if an object has negative velocity, it's going backwards, and its acceleration is negative, it's just going backwards faster and faster. Okay, the most obvious speeding up is when you have positive velocity, positive acceleration. But yeah, so that's the idea for B. You can look at the absolute value of velocity for speed, and like if you just looked at a graph of absolute value velocity, so just math, then absolute value of the velocity function. Now I'm going to press enter on y2 and y1, the equal signs, and that'll turn the graph off. And if I look here, see the graph of speed is going up. So the speed is definitely increasing from 3 to 4.5. So I'm happy with our answer. All right, moving on to part C. Total distance is the integral of speed. Okay, so the integral of absolute value velocity will tell you distance traveled. So this, we just type into the calculator, and we're going from 0 to 4. From 0 to 4. Equals, so now velocity we wrote in the y1, but I just wrote absolute value velocity in the y3 spot. So I can just go math 9, 0 to 4 of y3. So I have it saved in the y3 spot. Okay, and this is going to give us 2.387. All right, so 2.387. All right, this question is definitely faster than the other one. All right, now position at time 4. If you just know how to do this, like you're just like, oh, like I could just fly here, then you're going to say the position, are they calling it x of t? Yeah, they are. So they told us x of 0 equals 2. So that's the initial position. So here, all I have to say then is that x of 4. So I'm trying to salvage that. Yeah, I think after this question, I'm going to switch over to notability because this is like also painful. Okay, so we have x of 0. It might be lag because so many people are here, which is awesome. I mean, that's a great problem to have. Like, hey, so many people are at this live stream, so my computer is not able to handle it. Someday I'm going to have to upgrade my computer, I guess. But my computer is like pretty decent. All right. So here, just to explain this concept, the integral of velocity tells you displacement. Okay. So displacement is change in position. Yeah, this is like torture. Change in position. Okay, so this is change in position from 0 to 4, but it's relative to where we start. We have to leave this here. If that doesn't do it justice, just think of the fundamental theorem of calculus. Okay, that if I do the integral of velocity from 0 to 4, the fundamental theorem of calculus tells us to antiderive and plug in the upper lower limits and subtract. The antiderivative of velocity is position, so I get x of 4 minus x of 0. So if I want to solve for x of 4, I just add x of 0 to both sides. And now we just type it in. Okay. All right. All right, so x of 0 is 2 plus math 9, 0 to 4. And we're integrating velocity, which is saved in the y1 spot. Okay, so we get 3.432. All right, 3.432. All right, yeah, I'm definitely going to switch over to notability because it was not as bad as this. All right. All right, let me just put. All right, Stizzy, you're in timeout. Okay. Yeah, I kicked Stizzy. All right. Actually, yeah, I'm just going to like. Cool. All righty. So for the next part here, let me just see. I'm going to open up notability. So yeah, you could just ask questions in the chat and I'm happy to chime in. Let me just open OBS. I'm going to turn this off. I'm just switching programs because that program is annoying me. It's not working as well as I wanted it to work. So I'm going to just switch to notability and hopefully this one can handle it. All right, so this will have to do. I'm going to close. Yeah, GoodNotes had a good run, but it just wasn't. It was not holding up. Yeah, there's always at least one troll on like the big live streams. But I mean, what can we do? They're just, yeah, always going to be trolls. Okay. Yeah, remember the community guidelines here or streaming guidelines. Just be respectful in the chat. If you're just spamming, like a joke here and there, I like humor, but if you're just like being silly the whole time and just spamming the chat, you're going to get booted. So, all right. So moving on now to, let me just see. Yep, we could all see, right? No calculator. So we look over here. First thing we're going to do is find g of -1. So g of -1, we have a graph of f, and f is in our integral here. So g of x is an area function. That's what we call it. So for part A, I'm going to have g of -1 equals the integral from 0 to -1 of f of t dt. Okay, so here, the integral from well, I'm going to first find this area, and then I'm going to talk about the trap here. Just be careful of that. So the area of a triangle is 1/2 base times height. So I'm doing 1 times 3 divided by 2. So 1 times 3 divided by 2 is 3/2. But be careful here. Don't just say 3/2. The lower limit here is 0, and the upper limit is -1. We could flip those so that the smaller number goes to the bottom. And now we could treat this as normal. We're just going to say minus, and then the area from -1 to 0 is 3 over 2 since that area is above. Okay, so for the first part of this question here, we're going to have -3/2. Now, g prime of -1 is using the idea that the derivative g prime, so g prime is equal to f of x. Okay, so g prime is equal to f of x. And now for the next phase, we're going to use that information to answer the next part. Oh, at Michael Kaufman, thank you so much for the tip. I appreciate you all so much, but I do appreciate that. That's so cool, like knowing. Yeah, thank you. Just that's the short, is just thank you so much. I appreciate you. So here, g prime of -1 is, I'm just using what we have over here, is f of -1. And f of -1 is the y value at x equals -1. And the y value here is 0. Okay, so that's for that part. And now for g double at -1, g double, if g prime is f, then g double is equal to f prime at -1. And f prime at -1 is the slope of the function at this point. And notice here that it's a straight line segment. It's a piecewise linear function here. So if I just look at the slope, notice I'm going up 3 over 1. My slope here, I'm going up 3 over 1, is equal to 3. So f prime of -1 is just equal to 3. Okay, so we have, these are the 3 solutions here. Okay, so we have all of this here. And I'll write the point value here. This is going to go 3, 2, 2, 2. All right? So that one, these questions, if you know Unit 5, are not terrible. All right, I think this is like a very doable part of the test if you know your stuff. Like, it's not a lot of heavy math. Although, like, these could get nasty if it's like a semicircle, you know, and like you're finding the area between like a rectangle and a semicircle, or I'm sorry, a square and a semicircle. Then it gets a little annoying. Okay, on what values of x in the open interval -2, 2 is g increasing? So g increasing, I'm thinking of g prime greater than 0. Okay, if g prime is greater than 0, then g is increasing. But remember what we said over here, g prime is equal to f. So not only is this a graph of f, this is a graph of g prime. Okay, so we also have a graph of g prime. How did you get double prime? Double prime I got from deriving this. So if I have g prime of x equals f, then all I have to do is just derive both sides with respect to x. Okay, and the derivative of g prime is g double prime, and the derivative of f is f prime. Okay, so that's where that one is coming from. Hope that clears it up. All right, so now the next phase here, for what values of x in the open interval is g increasing? And we have to explain our reasoning. So g is increasing when g prime is positive. So now I'll erase the highlighted stuff. Where is the graph positive? And maybe I'll just erase all this stuff now so we could actually see. The graph is positive when the graph is above the x-axis. So from -1 to 1. Okay, so for what values of x is the graph of g increasing? We're going to say here from -1 to 1. Okay, so I'm going to say g is increasing. So g is increasing on -1, 1. And then we have because g prime is greater than 0 on those intervals. Okay, so because g prime is greater than 0 on those intervals. Cool. And this would get us the credit for b. Now we want to know for what values of x on the interval -2, 2 is the graph of g concave down. So concave down, we're looking for when is g double prime which is equal to f prime, when is that less than 0? Well, if this is a graph of f, when f prime is less than 0, so this is like the thought process. Like this leads me here. And then f prime less than 0 tells me to look for where is f decreasing. Okay, so I'm looking for where f is decreasing. So that's what we're looking for here. And f is decreasing from 0 to 2. All right, we'll see that here. F is decreasing from 0 to 2. So that's going to be our solution here. We're going to say that G is concave down, which I'll abbreviate for now, on 0, 2, because, and I'll just make, some space. And there's a few ways we could wrap this up. One way would say because F is decreasing on that interval. Okay, so F, which F is decreasing on that interval. You could even say G double is less than 0 on that interval, but I could say F is decreasing. Okay, F, which is equal to G prime, is decreasing. You don't have to say F equals G prime. That's just more than one way of saying it. Okay, so this is getting us to full credit. And now, the best part, sketching this. Okay, so sketching this is going to be something they don't really ask anymore. This is an older question, but I still think it's a useful skill to have. That's why I was like, you know what, let me put this on the live stream. So now to sketch this. So for this, I want to think about for part D, which I'm eventually just going to sketch it over here. But when I want to sketch this, I'm thinking about the significant values, the transition points, where the first derivative or the second derivative changes sign. So I'm looking here from -2 to +2. And I have a graph of f, which is a graph of g prime. So I want to look at the sign of g prime and g double prime. So the significant values are going to be at -1, 0, and 1. And now notice that g prime is negative. Okay, so I'll say g prime, I'll put that in purple. G prime is negative from -2 to -1. Then it's positive. And then from 1 to 2, it goes negative again. And then g double prime is positive from -2 to 0 because g prime is increasing. And then g double prime is negative, like we said in part C, for the remainder. And now I talked about this on the live stream day 1, I believe. It was day 1, that when your first derivative is negative and your second derivative is positive, your curve looks like this. It's decreasing and concave up. So it's decreasing with a smile. Then if you're plus plus, you're increasing and concave up. Plus minus is increasing concave down, and then minus minus is decreasing concave down. So this is the shape of the graph. They were going to give us space, but I'll just sketch this off to the side. And now some of the values here that I would want to know is what is something like g of -2? What is g of -1 we found? G of -1 was -3/2. So I'll just put the sketch, off in this space over here. So I have 1, I have 2, and this graph here, I'm just going to include these values like this. So sketch, it doesn't have to be perfect. And this is really all we're going to need here. Okay, so this is a sketch of g. So one of the values we already have, we found g of -1 was -3/2. So that's going to be about this location here. Okay, so that's g of -1. If I want to find, like, let's say g of -2, g of -2 is the integral from 0 to -2 of the function f. And notice that this is just a straight line, and the area from -2 to 0 are two triangles that are equal and opposite. So this is just equal to 0. So g of -2 is equal to 0. And by the same reasoning, g of 2 is also equal to 0. I could say g of 2 is also equal to 0 because if we look here, let's say I just write a 2 here for a moment. The area from 0 to 2 are two triangles that are equal and opposite. Okay, so this is also 0 over here. And if I want to find g of 1 is the area from 0 to 1, and g of 1 would be positive 3 over 2. Okay, so g of 1 would be positive 3 over 2. So all of those triangles have area 3 over 2. So this would put us here. All right, and then I'll put this one here. And then if you think about it, g of 0, I'll erase this. G of 0 is just 0. So I could use that area function to find all of these points. And now I use the 4 shapes. From -2 to -1, it looks like this. So maybe now I'll graph this in red. So we're going here 1. Then it's increasing with a smile. And then increasing with a frown. And decreasing with the frown. All right, something like that. All right. Yeah, this is good. All right. Yeah, I knew that question was going to be a little rough, that last part. But like it's old school, but it's a good question. Okay. Cool. So now situations like this, area and volume, and we get a calculator. So I know unit 8 is usually like people complain about it. It's tough. So here we have f, and this is f of x. And we have g of x. Okay, g of x looks like this. So I'm going to go over to the calculator. Oh, in part C, why don't you just say g double prime? Why don't you just justify by saying, oh, the heart is covering what you're trying to say. Justify by saying g double prime is equal to f prime. Yeah, I mean, you could say, because g double prime is negative, you can say that. That's fine. I just wanted to use the thinking that we were looking for. Like, oh, the graph is decreasing. G prime is decreasing from 0 to 2. But that works also. And look, that's the beauty of math. There's more than one way that you could get to the correct answer. All right, so, all right. Moving on to the area question. So f of x, the top function here is 1 plus sine 2x. Make sure you're in radians for the whole test. Okay, don't graph this in degrees. And then you have e to the x over 2. E to the x over 2. And I'll clear this out. I'm going to press zoom 6 just to put this back to normal. And I'm like, oh no, I didn't bring my reading glasses. So I press zoom number 1. Zoom box. And now watch this. I go over and a little bit down, and then I crop the photo. I press enter. I go up. I go over. And from here, I scroll down a little bit. Press enter again. And there's a much better picture. I need to know this point of intersection. That one is at x equals 0. This one, though, is not as obvious. Second trace 5. And whoops, second trace number 5 for the intersection. I get close. I press enter 3 times. Okay, and then that's our intersection. I press second mode to quit. And then second minus sign for the answer. And there's the answer. I'm going to store that as the letter A because I don't feel like retyping that over and over. Okay, so now let's just borrow this. And we'll crop this photo so that we could use it. All right. So here, now we move on. From this step, find the area of R. The concept that we need here is that the area between two curves, if I use cross sections, I take a slice like this, is a rectangle. The vertical distance of this rectangle is the top function minus the bottom function. Okay, and I think of this as an infinitesimal, like a thin slice of area. So for A, the area of one slice is f of x minus g of x, and then dx. And then from here, the full area would be from 0 to that value here. So I would just point out point spread, this is 2, 3, 3. And you might say, wait a minute, 2, 3, 3 is only 8. And that's because writing down this value here like if I just say here, like this x is, I'll call it x1, is equal to that whole mess, that gets me my 9th point. Okay, so just knowing to trace this. Let me make sure I wrote it right. 3, 5, 6, 9, 2, 5, 3, 5. Cool. So here, if I define x1 like this, I could write x1 over here. So I'm integrating from 0 to x1. All right, so if you name the point like this, then you could just type it in like that. And now this tells us that the area of R equals, and let's just see. We have math 9, 0 to A, and we have the difference of the function. So I have alpha trace y1 minus alpha trace y2. And now I press enter and 0.429. Okay, so 0.429 is our solution. Cool. Find the volume of the solid generated when R is revolved about the x-axis. So if we're spinning this about the x-axis, so I take this is my axis of revolution. Then I have to look for my outer radius and my inner radius. So my outer radius is the distance from here to here. The outer radius is f of x, and f of x is the whole thing here, because technically this is the line y equals 0. So the concept I like to use is when you're finding vertical distance is I just say, oh, top minus bottom. 8 minus 5 is 3. So these numbers are 3 away from each other. So if I do top minus bottom, I'm doing f of x minus 0 is f of x. And now for the inner radius is the distance from the axis of revolution. The axis, just remember, really big idea. The axis, this is your center. Okay, this is what we're spinning around. And that is going to tell us also our inner radius. Our inner radius is going to be g of x. So then for part B, all we have to do is say that the volume is pi, and then I have the outer radius squared. So I have outer radius squared minus the inner radius squared dx, and I'm going from 0 to x1. All right, please don't do f minus g squared. Common mistake is people do this. Don't do that though. Okay, that's bad. All right, now just math 9. So here we go. So pi, and then math 9. We're going from 0 to, we saved it as a, so we get to reuse that again. And now I have alpha trace y1 squared. That's why I like typing it in with the shortcut, because then it's just easier. I don't have to keep retyping all that. And it's 4.267. If you're bad at rounding, you could just chop 3 decimal places and you also get it correct. I could say 4.266 or 4.267. All right, so 4.267. All right, I'll round. We'll make our 5th grade teachers proud. All right. So the next part. Now we have region R is the base of a solid. And for this solid, let me erase some of this stuff. So for the next one, what we have is the base of the solid is region R. And the cross sections perpendicular to the x-axis are semicircles with diameters extending from f of x to g of x. Okay. So here, this is maybe tricky to imagine, but imagine I put R on the floor. So here's R, and my cross sections are going this way. So I just imagine my cross sections, I'm making them into semicircles. I can't imagine what this looks like. I mean, it kind of looks like a croissant, maybe sushi. I do like sushi. All right, I get yellowtail, and I get shrimp tempura and spicy tuna. So you want, you could write your favorite sushi roll in the chat. But if I just keep drawing semicircles, yeah, maybe a croissant or a sushi, one of those. Okay. But the concept of Unit 8, one of the big ideas is we only need one cross-section and it tells us everything that we need to know. So here, I take one of these cross-sections out and I say, all right, there's my semicircle. They told us the diameter extends from F to G. So the diameter of this thing is F of X minus G of X. Okay, that is the distance, the vertical distance from F to G, just F minus G. This is dx. So then the volume of one slice, if the diameter is this, the radius is F minus G over 2. So is F minus G divided by 2. So the volume of a semicircle solid like this is pi times radius squared dx, but I have to divide by 2 because it's a semicircle. Okay, I have the diameter and I divide that by 2 to get the radius. But then I have to I pretend this is full circle, pi r squared, and then I divide that by 2 as well. So the semicircle is the one people mess up the most in Unit 8. That's why I chose it for the live stream, just in case you get a semicircle. Okay, so there's our integrand. Okay, so now for the full volume, I'm going to take pi over 2 out. And now we're going from 0 to x1. And now we have f of x minus g of x over 2 squared dx. All right, and now let's just not make a typo. That's like most of the battle. All right, but just be extra careful with those semicircles. Okay, so I'm going to press alpha y equals enter just so it looks nice. Pi over 2. And then we've got math 9. From 0 to x1 is still saved as a. We use that 3 times here. And now parenthesis, alpha y equals enter. F is alpha trace y1 minus g is alpha trace y2 over 2. I hit the right arrow, close the parenthesis, then square it. Just be careful with your parentheses because they do have the potential to like really just wreck one of your questions. And this works out to 0.078. Okay, so 0.078. One more down. All right, we're making nice progress. We got through 4 questions. Yeah, so at Jordan Go, you could write it as pi over 8, but in the free response, especially when you have a calculator, you just leave it and just type it all. Oh, Vin, why pi over 2? Because it's a semicircle. So for one, the diameter is F minus G. Okay, so F minus G tells me the diameter. Because all of these, like here, like that red I just drew, let's say it's this one. Okay, so the red piece that I just highlighted and just drew over again, that's like the bottom part. And that's the diameter lying in region R. And the diameter is F minus G, but the radius is half of the diameter, so I divide that by 2. However, when I think of the area of this, I think of pi r squared. Okay, like if this was a disk, like if it was like this, I'd be like, oh, pi r squared dx, but this is like someone chopped it in half. So that's why I'm dividing that by 2. Okay. All right, so moving on to the Riemann sum question. So popular question, they say to estimate and then show the work that leads to your answer, indicate units of measure. So we're estimating. So t prime of 7, this is the instantaneous rate of change. Okay, slope of the tangent line. And what I think of, if I were to just do a sketch of this, so 0, 100. So this is t of x. So 0, 100. 1 is up here at 93. Not drawn to scale. I'm just drawing this for the sake of drawing it. 570. Then we have 6. And then 62. And then we have 8 and 55. Okay, let's say the curve that connects this And did they say it's strictly decreasing? Oh, t is decreasing. Okay. So if it's decreasing, it can never go back up. So something like this. So what we're trying to do is estimate the derivative at 7. Okay, but we don't have an explicit function for t of x. So what we're going to do is pick the 2 points that get us as close as possible. So we're going to pick these two. Okay, these 2 points at 6 and 8. And if we find the slope of the secant line that connects those two, we're going to say that's close enough to the tangent line. So that's the concept. So this is roughly equal to, and we're going to have t of 8 minus t of 6 over 8 minus 6. And the units, the t values, they tell you the units are, they give them in the table. It's degrees Celsius. So in the top here, I'm going to write degrees Celsius per, and then in the denominator, we have centimeter. Okay, so per centimeter. And now we just simplify 55 minus 62. That's going to give us negative 7 over 2 degrees Celsius per centimeter. And this is negative 3.5 degrees Celsius per centimeter. This was actually a calculator question. I had to double check it to be safe, but it is. All right. So that gets us the credit for A. All right. Cool. All right. Questions. Let's see. So no need for second. Oh, predictions. Yeah, I mean, the predictions, I mean, the questions I have in front of you, I think are pretty standard. The only difference is for the BC. BC, I think it's going to be polar this year. I hope it's free response. I hope it's parametric, because most people find parametric to be easier. But I really do think it's going to be polar, because they're overdue. But for Calc AB, I'll say rate in, rate out. And then like a particle question. Graph of F prime, definitely. Differential equation for question 5. Question 4, do they go with area volume? I mean, maybe they could do area volume. And then like question 6 is like miscellaneous. Like, it could just be like, what do they like to throw in there? Like a L'Hopital combined with maybe a squeeze theorem. They haven't done squeeze theorem in a while. Squeeze theorem is the underdog. Yeah, polar is tough. I know, because people don't like trig. I joke with my own students. I'm like, hey, we could laugh about not knowing trig, but then the smiles are going to start to fade around late April. But you get a calculator, so that could really carry you a bunch, except in the no calculator. All right, write an integral expression in terms of t of x for average. All right, here we go. Average temperature. So integral expression in terms of t of x for the average temperature of the wire. So the temperature of the wire is t of x. So the average temperature would be 1 over 8 minus 0, integral 0 to 8 of t of x. Okay, and then this equals, I'm going to have 1/8 times, and then they tell us to estimate. So I shouldn't say equals. I'm going to say roughly. So it's roughly equal to, and 1/8. And now I have to use 4 subintervals. Now, that's one of the benefits also of drawing this out, is that if you struggle with this part, then what you could do is you could draw it out and then just draw in some trapezoids here. So what I mean by that is I connect this one and this one, and there's my first trapezoid. Then I connect this one and this one, and there's my second trapezoid. There's my third, and there's my fourth. If you know how to just do this by the table, then just do this by the table. But remember, a trapezoid, the parallel sides are the bases. And the area of a trapezoid is 1/2 height, base 1 plus base 2. Okay? So that's something to know. And that, if we know this formula, then it's just geometry, and we just run with it. So here, we're going to have 1/2. But in calculus, the height is delta x, and then these are the y values. And whoops. So these are the y values. So let me just do this for now to say y values. And let me check the stream for a second. I want to see if, yeah, that's cut off. So let me just scroll up a little bit. So those are the y values. All right, and that was a little sloppy. Let me just fix that. So the y values. Okay, so that's the concept that you need. All right, so if I use the picture that I just made over here, then all I have to say then is I have 1/2. The height is delta x, and the change in x, if we even just focus, we could just look like from here to here. The change in x is equal to 1. So I have 1/2 times 1. And then I have the sum of the y values is 100 plus 93. So that's 193. All right, plus 1/2 times the new delta x. Now I shift my focus here. And my new delta x is 4. And then I do the sum of these y values, 93 and 70. That's base 1 plus base 2. And that's going to give us 163. And then I have plus 1/2 times the new delta x for the third subinterval is 1. 5 to 6 is a jump of 1. Now the sum of the y values, 70 plus 62 is 132. And then finally, 1/2 times 2 times the sum of the y values. You could do 62 plus 55. And let me see how to do this carefully. Hang on, I could do this. Yeah, that'll do it. All right, cool. So the delta x is 2, and then 62 plus 55 is 117. Okay. But remember, AP test, don't simplify. In 2024, this is a no calculator question. If it's no calculator, you don't have to simplify it. You just leave it like this and just hope for the best. Okay. If you do simplify it, this is the benefit of simplifying is that if you're not sure how to interpret it, simplifying makes it make sense. You're like, all right, 75.688. All right. And I won't, I guess, show how to do arithmetic and the calculus. Like that, I know people could type probably fine. So here, we indicate units of measure. And do they ask us to interpret this? No, we don't have to interpret this. So I'm not going to interpret it. I'm just going to leave it as is. All right. But what this, yeah, oh, actually interpret it. They told us it's the average temperature of the wire. So there's the interpretation. Sorry, I've been teaching math for like so many days straight, and then like at night, like my thinking is a little choppy. So, all right, let's just see here. So part C. All right, part C is so easy, it's difficult. If you know the fundamental theorem of calculus, this is easy. If you overthink it, it's going to be worse. So here, I just use, you don't have to say that you're using the fundamental theorem of calculus, but it's the antiderivative of t prime. The antiderivative of t prime is t, and then I plug in 8, 0 to the function and subtract. So this is the fundamental theorem of calculus. And now t of 8 minus t of 0, that's 55 minus 100. Okay, so 55 minus 100, which is minus 45. Okay, indicate units of measure. So for here, if I have to indicate units of measure, I'll say that this is degrees Celsius. Okay, so we'll say minus 45 degrees Celsius. And now we have to interpret this, or explain it in terms of the temperature of the wire. Okay, so we have to explain the meaning of this in terms of the temperature of the wire. And just think about it. If we read the question here, they told us that the table gives selected values of some wire. So let's just say here that we have like some wire like this. And at one end, the temperature of the wire is 100 degrees Celsius. And at the other end, 8 centimeters. So this is 8 centimeters. The temperature of the wire is 55 degrees Celsius. Okay. And if you think about like they said like it's heated. So the heat source, like, I don't know, it's like heating it at this end. Like something is like, I don't know, shooting fire at it for some reason. Whatever. It's heating up over here. So it's 100 degrees Celsius. And then as it travels down, it starts to cool. And the coolest end is at 55. So what is the meaning of this in terms of the temperature of the wire? It tells us here that the temperature from the heated end changes, it decreases by 45 degrees Celsius to the other end of the wire. Okay, so that's just something I would say and write out in some form. So I'll just write that now, and then I'll have to shrink everything down. So I'll just say that the temperature, I'll abbreviate, of the wire decreases okay, because remember, a bigger idea too is the integral of the rate tells you the net change of the function. So the temperature changes, it decreases by 45 degrees. So the temperature of the wire decreases by 45 degrees as we go from the heated end. So from the heated end to the opposite end. Okay, so that's the idea. There's a phrase or quote I like to share with my students, an Abraham Lincoln quote that says, "You give me 6 hours to chop down a tree. So give me 6 hours to chop down a tree, and I'm gonna spend 4 hours sharpening the axe." And I like to share that one because for these kind of questions, like when they ask you to explain, you got to spend some time sharpening the axe. Like, don't just write the first thing that comes to mind. Like, think about it and then start writing. If they tell you, like, hey, what's the derivative of x squared? You'll just be like, 2x. You're not going to sharpen the axe for 4 hours. That's not a sharpen the axe question. But this one, you got to sharpen the axe a bit. Think about it. Sometimes I have to reread. There's no shame in that. It's not like you only get one shot at reading it. And if you don't understand it, you move on. Like, read it a few times. Ooh, part D. All right, part D is kind of mean. So here, this is like MVT on steroids a little bit, the mean value theorem. So we'll take a look. So here, I'm just going to clear this out so we have the space. And are the data in the table consistent with the assertion that T double prime is greater than 0 for every x on 0, 8? So if T double prime is greater than 0, like the whole time, then that would mean T is concave up. Okay, so T is concave up. All right, that's what we're trying to see. Is it happening? Well, all I have to look for here is for the average rate of change to not increase. Because concave up, what it means in terms of a derivative is that the slope is increasing. Okay, so this just means, once again, yeah, the slope is increasing. The derivative is increasing. So I look here, and I'm just doing some math in my head, but I find, let's say, the average rate of change. I'm going to write it like this, and I'll zoom out because you all have a copy of this, so it shouldn't be too bad to keep track of. So the average rate of change of T of x on 0, 1. So this one here, the average rate of change is -7. So I'm just going to like look at all of these, like average rate of change of T of x on the next interval from 1 to 5. And I promise this has a purpose. I'm going to find the slope again. And I promise if we do, this is decreasing by 13, -13 over 4 is going to give us, let's just see. Oh, wait, I'm sorry. Let me just see here. This works out to, just thinking out. I'm going to use, we have a calculator. So like, why am I, doing this by hand? So let me just, like, there's no, whoops, let me switch it back to the view. And I promise there's a point to this. All right. This is going to build up to something. So I might as well just find these all right now. So alpha y equals enter. Yeah, 70 minus 93 is 23 divided by 4. Yeah, so 70 over 5 minus 1 is this. And then if I do one more, So let's say now I do 62 minus 70. And once again, you'll see why I'm doing this in a moment. This was a hard question. I tell my students in person, I call some of these questions statue questions. And the reason why I call it a statue is that if you get a 108 on the AP test, your school will probably build a statue of you in front. You know, like you'll be famous forever. You could write a book and just give people advice, no matter how good or bad, on how to get a 5 on the AP test. Like if you get a 108, you make a video, you're going to just automatically get 1 million views. So like, good for you. So a question like this is like borderlines. Like this is like a statue mean value theorem. Okay. So it's not polite at all. It's a hard question, but I'm going to, break it down anyway. I'm not going to skip the worst parts of this. We're going to go through it. So the average rate of change from 1 to 5 is negative 5.75. And now one more time, the average rate of change of t of x on the interval 5, 6, and then I'll make my point. The average rate of change here is negative 8. So notice that from here to here, it increases. And that's good for concave up. If your average rate of change is going up, that's suggestive of concave up. However, from here to here, it decreases. Okay, so there it is. Okay, that's what disqualifies this as not being concave up over the entire space. But now, how do we write that in a sentence from 0 to 8? Well, we're going to use MVT. So here, the way we could say it, all right, is we're going to say, so we'll just get to writing here. I'm going to first say no. Is the data consistent with this? I'm going to say no. Disagree. All right. Why? The average rate of change on 1.5 is, and now we're just going to say here, negative 5.75. So what that suggests here, because I don't need this one, I need to show that it decreases. Because if t double prime is greater than 0, then that means that t prime would be increasing. Okay, that t prime is strictly increasing. So I don't really need to mention this one where there was an increase. I need to target these two where the decrease happened. Like this one and this one are the ones I'm going to put in the explanation here. And you'll see where this is going, hopefully. So the average rate of change on 1.5 is this. Okay, so the average rate of change, we'll just say, also of t of x. So the average rate of change of t of x. Let me just squeeze this. So, oops, the average. Okay, so the average rate of change of t of x on 1.5 is this. So by, or how about I say therefore? Therefore, by MVT, okay, there exists, and I'll call the first point C1. There exists a value C1 between 1 and 5, such that, and now we're just going to conclude here that T prime of C1 equals negative 5.75. Okay, and then I'm going to mention this one. And then next we have the average rate of change of T of x on the next interval, 5, 6, is negative 8. So now we can say here, or I should say comma. So therefore, by MVT, backwards E means there exists. There exists another value, this time between 5 and 6, such that the derivative at the second one is negative 8. Now, let's think about the significance of this. All right, once again, this I am calling a statue. This is definitely not the most polite question we've seen so far. I'm going to shrink this down just so that we have the space, because this question deserves it. Okay, this is for the 108s. All right, if one of you get a 108, just give me a shout out. I'm just kidding. You don't have to give me a shout out. You just enjoy your fame then. Okay, so here, think about what this and this means together. That t prime of C1, and let me just write here C1. I forgot my subscript. C1 is between 1 and 5. C2 is between 5 and 6. So think about what this means. T prime of C1 equals this, and T prime of C2 is equal to -8. So if we piece that all together, if at some point the slope of the tangent line decreases, that tells us that T double prime greater than 0 is not possible. Okay, so since T prime of C1 equals this, T prime of C2 equals this, and we can say confidently here that C1 is less than C2. C1 is between 1 and 5, and C2 is between 5 and 6. So if this is true, and C1 is less than C2, then that tells us at some point T prime of X is decreasing. Therefore, T double prime greater than 0 on 0,8 is not possible. That is a hard question. That is very mean. That's why they call it the mean value. No, that one was kind of brutal. Now, look, maybe one extra thing I would say here, like just in case they want to play I gotcha, T is decreasing and twice differentiable. Maybe I'll just like this is like a 108 detail. Like I want that 108 just in case. You could say this, like T twice differentiable means T is differentiable, and that means T is continuous. Okay, because technically I can't use mean value theorem unless my function is continuous on a closed interval and differentiable on the open. But that would get us full credit. That was pretty awful. Not gonna lie. Thank you for sticking with me through that. And thank you, 108 people on this. This is just so cool. Yeah, just thank you all for being here. This is like just really awesome. I'm not the mushiest person in the world, but I am very grateful for all of you. Like it's pretty awesome. This is like an exciting time of year, even though it's like an exhausting time of year. It's cool to have everybody on board. All right. Am I gonna save this? Yeah, I'm gonna save this. If that showed up. All right. Comparing apples and camels. I like that. Did the test get leaked? No, I'm not gonna risk my health insurance for leaking this. Yeah, that didn't happen. These are old questions. 2006. All right, differential equation. And this is, I believe, is it the last? Oh, wow, this is the last AB question. So if AB people leave me after this, I understand. Just know I did save my day 1, day 2 live streams. So you can check those out. Sorry, just getting some water. You can check those out on my, channel. Okay, let's see. Go to the previous. Oh, inner and outer radius is hard for you to conceptualize. Yeah. So inner outer radius, I could talk about that. How did I get that? Where am I? Oh, this one, part B. Yeah. So inner outer radius, the concepts I usually send my students to watch. Let me see. Do I have it? All right. This is for you. Let's see. Do I have it here? Oh, that'd be so good if I have it here. Let me just see. Do I have? All right, ready? Okay. So this helps, hopefully. All right. So inner outer radius. I show my students this. It's a little ridiculous, but the axis of revolution is the hang on, let's start that over. It's a good movie. The axis of revolution is this. Okay. So here, let me go back to this now. Yeah, my do now on unit 8 is just stare at the chickens for 5 minutes and think about what it means to rotate something. So here, I'll do this part. I'll just explain the concept. So the center, if I spin this around, I'm imagining some solid here. This is like our chicken. Okay, so here's our chicken. And the outer radius goes from the center all the way to the end. Okay, so that was a terrible curly bracket. Let me try again. And the concept is this. When you want to find the vertical distance, you do the top thing minus the bottom thing. So here, the top is y equals f of x, and the bottom, the x-axis, is y equals 0. So my outer radius, and I'll erase this, my outer radius, get those out of here, is the top, y equals f of x, minus the bottom is y equals 0. My inner radius goes from the center, so it goes from here to the beginning of region R. So this curve here is y equals g of x. So now I use that top minus bottom concept, and I'm doing the top thing, g of x, and then minus 0. Okay? So that's that. Yeah, tricky question for sure to deal with. All right. So yeah, that is the concept. Oh, rotisserie, sorry, hungry now. Yeah, Costco rotisserie chickens is like one of the greatest things ever. $5. Every time I go to Costco, like I have to get a rotisserie chicken. Even if I had like, dinner like 12 minutes ago, like I still have to I just can't not get it. It's $5. Yeah. So, all right. This one's tedious. So I'm just saying this is tedious. And be careful. Like they're not going to bring a magnifying glass to the AP test to like measure. But here, basically what we're doing is to build the slope field, we have to plug in 9 points to the derivative and then sketch the slope. So here it helps to know our friend slope guy. Okay, slope guy, when you have a positive slope, the line goes up. A negative slope, the line goes down. When you have a vertical line, your slope is undefined, and a horizontal line has a 0 slope. So here, I look for things like, okay, dy dx, this piece here jumps out. So you got to look for patterns. Patterns help. When y equals 1, so I'll just write this carefully, y equals 1 implies that dy dx is 0. Okay, because if I do 1 minus 1 squared, I get 0. So every time y is equal to 1, so now I'm focusing on y equals 1, which is like here. All of these points have a 0 slope, and think of slope guy. The slope is going to be like this. Okay, now in terms of the point spread here, this is 2 points, 1 point, 6 point. So just doing this row gets you 1. The other 6 are worth a point. So as long as you get the direction right, you'll be fine. Yeah, slope fields. It's so tedious. It's like, ugh. Like, all right, like now I just honestly just take each point one by one. I'm like, all right, 1, 0. If I plug in to y prime, I'm going to have -1 squared, and then I have cosine of pi. And this is going to give me -1. Okay, so -1. What I do for the slope field too is a slope of -1, I think going like down 1 to the right 1 or up 1 to the left 1. And I aim for this. So I like to aim for something. Now, if I do this for the other points, like let's say, you don't have to show this, by the way. This could all happen in your head. Okay, this could all happen in your head. Okay, they're not saying like, oh, now just sketch the slope field. They're not like, you don't have to show this work. If you want to show it, you can, but you don't have to. If I plug in 0, 0, I get cosine of 0 is 1. -1 squared is 1. So I get a slope of 1. So here I get a slope of 1. Okay, and then if I plug in -1, 0, x is -1, gives me cosine -pi, which is -1. And y equals 0 gives me -1 squared is 1, and 1 times -1 is -1. So this would look like this. Okay, decreasing towards here. Now for this row, I'm plugging in, let's say I do 0, -1 next. So if I plug in 0 and I plug in -1, I get -2 squared is 4 times cosine 0 is 1, and so -2 squared is 4 times 1 is +4. So I have a slope of 4. So I'm imagining up 1, 2, 3, 4 over 1. So I'm like aiming for here. And I'm like, all right. So there's the line. As long as you make it steep, like I said, they're not taking out a magnifying glass, you'll be okay. And now 1, -1 is going to give us, so I'll just write it over here so we can visualize it better. So if I plug in x is 1 and y is -1, I get -2 squared is 4, cosine of pi is -1. So I get -4. So that's up 1, 2, 3, 4 over 1. I'm doing something steep like this. Okay, steeply negative. And then -1, -1, I just make that a -1. Cosine -pi is -1. And then -1 squared is 4. So this is -4. So steeply negative. And that would get us 2 points. Okay, not pleasant. All right, so I'm glad that's over. For the next part, B, now we have a horizontal line with the equation y equals c satisfies this differential equation. Find the value of c. Look, the sneaky way, see how these are all horizontal? If we use this, remember what we said before, when y equals 1, the derivative is equal to 0. So all of these, if I sketch a solution through here, let's say I sketch the solution this way, like this is our solution. This is our horizontal line solution. And this was only worth 1 point. So honestly, I could just say like, oh, y equals c here, like I could just say that c equals 1. And that would get us full credit, honestly. Otherwise, what I could say is like y equals c is a solution implies dy dx is equal to 0 because I'm deriving a constant. And then here I could set dy dx equal to 0. So this implies that 0 equals y minus 1 squared times cosine pi x. However, if I'm looking here that y equals c is a solution, then that tells us here that we could target this piece and say, oh, well, this tells us here then that y minus 1 is equal to 0, which then y equals 1. Like this is our horizontal line. So this is like just extra saying all this over here. Like once again, this is extra. That's only worth 1 point. So I could have just used the slope field to get the answer. Okay, remember, you could sketch solutions through a slope field, and that's valid. All right, but this might just bring you more peace of mind. All right, and then this is standard, the 6-point separation of variables. Okay, you have to know how to do this. This one here, part C, like I'll triple star it, okay, is so important. Just this, here's the advice. Yeah, you have to know separation of variables. right? If you spell separation wrong, -1. No, I'm just kidding. But a lot of people spell it S-E-P-E. It's S-E-P-A. I feel like I used to spell it wrong, and then like I was like, whoa, there's an A there. So okay, separation of variables. Okay, and advice is, so know this topic well, because it's worth 6 points. Like if you can't even get started here, you're starting off -6, and this will wreck your free response score. All right, and the advice is be awesome at anti-derivatives. So basically, like, yeah, unit 6. And algebra, like, yes, but not as important. Okay, so now let's actually do this. So I'm just going to write down the differential. So part C, we have dy dx equals y minus 1 squared. Then we have cosine of pi x. So separation of variables tells us to get the y stuff together and the x stuff together. So I want to get this with this, and I want to get this with this. Okay, those belong together. So here, and let me just move this out of the way. I'm going to multiply both sides by dx. And I'm going to divide both sides by y minus 1 squared. Okay, y minus 1 squared. And this is gone. This is gone. And now look what we have. We have dy over y minus 1 squared equals cosine pi x dx. Okay, so this is where we are. Now, we integrate both sides. Separation of variables is 1 point. So this is 1 point. Now we do this. Please don't do this. This, if you do, LOL, please don't. Don't say natural log of this. Common mistake. Don't do it, please. A lot of people do that because they just see a fraction and they're like, natural log. But no, you only do that when it's to the first power. Okay, so don't, someone in the world is going to do that. So sorry to that person. But no one here, right? Because I just warned you. All right, so y minus 1 to the negative 2 dy equals cosine pi x dx. So from here, now we're just going to complete this process. So we're going to do the power rule on this. Now you might say, wait a minute, I have to do a u substitution. But notice the derivative of y minus 1 is 1. So if you ever define a u term, so let's say you go, oh, I'm going to do u sub y minus 1. And du then is 1 dy. If your derivative is 1, that means you could skip u sub. Okay, so you're like, no, what? Never mind. I changed my mind. I don't want to do u sub because my derivative is 1. If your derivative is not 1, then technically, like, yeah, you could do the u sub. If your derivative is constant, there's shortcuts. Like for something like this, I just know from doing so many of these, which all of you probably did, especially for a separation of variables question, it's so exhausting. To have to do 2 u substitutions within is just so tiring. Okay, so just know that. Y minus 1, negative 2 plus 1 is negative 1. I divide by negative 1 and I get a minus here. And now on the right side, if I use this formula, is 1 over pi sine pi x and then plus c. Right, do not forget plus c. If you forget plus c, that just like ruins the whole question. Now I can get rid of that cool formula and I will group all of this stuff here. Okay, so let's just get this all together. That way I can make space. So group and shrink this down. Cool. Just so we have the space. Oops. All right, when I actually get the whole thing, I don't want to lose anything here. All right, perfect. So now the initial condition, f of 1 equals 0, that's the same thing as the point 1 comma 0. Okay, so I'm going to use this And let's just say I plug it in over here. So now I plug in, and yeah, I'll just say I'm going to do that over here. So this has a name. This is our general solution. So I personally like to plug in at this step. So if you solve for y wrong here, I find you could like wind up losing more points. Like it's better, I think, to just plug in here. So whoops. So general solution. Okay. So I have negative now. I have 1, 0. So I have 0 for y. See, this is like my x and y. X and y. So I have negative and then 0 minus 1 to the negative 1 equals, and we have on the right side 1 over pi sine of pi times x. X is 1, and pi times 1 is pi. And then plus 0. Sine of pi is 0, so that wipes out. And now this is negative 1 to the negative 1 equals c. So c equals negative 1 to the negative 1 is 1 over negative 1, but then with a minus in front, it's like times another negative 1. So this just makes positive 1. All right, so that's the algebra. So now that we have the value of c is equal to 1, we could plug it back in. We plug it back into the general solution. So we have minus y minus 1 to the minus 1 equals 1 over pi sine pi x, and then plus c, and c is equal to 1. So now from this point on, we have 5 out of 6. So the many steps of algebra that I'm about to do is only worth 1 point. So if you mess up here, yeah. Cool. So now, next, I'm going to multiply everything by negative 1. And I'm going to have y minus 1 to the minus 1 equals 1 over pi sine pi x, and then plus 1. So then here, to solve for y, I'm going to do next, I'm going to raise both sides to the negative first. And the reason I'm doing this is when I have a to the b to the c, this is a to the bc. So negative 1, I would just multiply those to get y minus 1. Okay, so we have y minus 1 is equal to, and if I raise this to the negative 1, I could leave it like this. I don't have to simplify. Okay, I could leave it in this mess here and it's fine. Okay, so if you prefer to leave it like this, then don't change it. Like, why mess it up if it looks this nice? And from here, yeah, I mean, whatever. I could leave it like this, but if you want to see how it matches the rubric, there's a little bit more stuff we could do. So we have y minus 1 now equals, and if I want to, I can say 1 over all of this. Okay, I could say it like this, and that's going to be fine. The one thing I should point out, though, there's like one step I should have mentioned. People probably caught it. Oh no, I really got to go back. When I multiplied, I went a little fast here. That I distributed the negative, I got to distribute it all the way across. I got to go minus here. Yeah, I mean, that's why I have my solutions next to me. Like, I worked this out ahead of time just in case doing this, sometimes I'll lose track of where I'm at. So negative 1 times the minus goes positive, but then I distribute the minus, they all become negative. And now I could do that algebra I just mentioned. So I'm going to raise this. We'll change colors. I'll raise all of this to the negative 1. Okay, but that algebra still applies. Okay, so now I have y minus 1 equals, and I could say 1 over negative 1 over pi, okay, sine pi x, and then all of that minus 1. All right, if you prefer, though, but you know what? We don't get points for simplifying. I would rather just play it safe. Just leave it like this. Like I said, you don't get extra credit if you actually simplify here. So now I just go plus 1 on both sides. And our final answer, I'll write this in red, is y equals, and now we have left over here, we're just going to have 1 plus. Okay, so I have 1 plus, and then this whole mess. All to the negative 1. Okay, so that's it. It's really all I have to worry about here. All right. So yeah, that's part C. And now that ends the AB part. So I'm going to move on now to 4 BC heavy questions. There is some AB related stuff here. Like parts A and B are Calc AB friendly, but C and D, yeah, you're not going to recognize if you took AB. All right. So 4 to go. And yeah, we're making a good pace here. All right. So the spread for this question, 2006 BC5, is 3222. So 3222. So we're going to find dy dx and the second derivative at -1, -4. So part A, I only here have to just plug in the point. So let's just see. Dy dx at -1, -4. And this is going to give us 5 times -1 squared minus 6 over -4 minus 2. Okay, so I'm plugging in -1, -4. And now this is going to give us, we have 5 times 1 is 5. And I have minus 6 over -6, which changes to 5 plus 1, which is equal to 6. Okay, so that's the beginning of A. For this part, second derivative, I have to derive the original equation. Okay, so I'm deriving dy dx equals this. And then we have minus, and I'm going to call it 6 times y minus 2 to the negative first, because I don't feel like using the quotient rule here. So this tells us now that our second derivative, d squared y over dx squared, is equal to, the derivative of 5x squared is 10x. That part is nice. This part I got to be careful. I got to use the chain rule. So I have -1 times -6 is positive 6. Y minus 2 to the -1 minus 1. But the derivative of the inside is not just 1. It's dy dx. Okay, so then to close out A, the second derivative at the point -1, -4 is equal to, I have 10 times -1 plus 6 times, I have -4 minus 2 to the -2. But then dy dx, the derivative at -1, -4, we just found from here is equal to 6. Okay, so this piece, like my head is going here, like, oh, this, I'm just borrowing. Okay, cool. So if we move on from here, now we have -10, and we have plus 6 times -6 to the -2, and then times 6. So this one here, I have -10, and then that's going to give us 6 times 6 is 36. And then -6 to the -2 is 1 over -6 squared. So now I have -10 plus -6 squared is 36, and 36 over 36 just cancels to make 1. So this works out to -9. That was worth 3 points. All right, so there was a lot going on here. And I will shrink this down. Actually, we might have space. Part B, though, honestly, I think part B is the worst. Out of all of them, part B is pretty tough. It's the most abstract. This one, you have to sharpen the axe, if you heard my analogy from before. But is it possible for the x-axis the x-axis is the line y equals 0, to be tangent to the graph of f at some point. Explain why or why not. So if you think about it, if the x-axis is the tangent line, at least what I'm thinking of is we have some function. If the x-axis is the tangent line, then two things are happening. The tangent line is y equals 0, okay? But not only is the tangent line y equals 0, the slope is also equal to 0. See, it's a horizontal tangent. So this is equal to 0, and dy dx, the slope is equal to 0. Okay, so the line is y equals 0. This is the equation, y equals 0. And the slope equals 0. But in calculus, the slope is the derivative, right? The derivative tells you the slope of the tangent line. Okay, so that is what you had to think about for part B, just to get started. So here, how we're going to deal with this, we'd say, is it possible for the x-axis to be tangent to the graph of f? Well, if the x-axis, so the x-axis tangent to f would imply that y is equal to 0 and dy dx is equal to 0. And now this, we'll just, yeah, the pen is freaking out a little. So then this one here would imply, so this implies then y equals 0, dy dx equals 0. If we go back to our original equation here, so dy dx is this whole mess here. So that would tell us 0 is equal to 5x squared minus 6 over, and then I have y is equal to 0, and then minus 2. So then this would tell us that 0 is equal to 5x squared, and then negative 6 divided by negative 2 is positive 3. But now think about this. So this equation here, so the equation, like over here, we could say, so the equation has no solution. I'll say it has no real solution. So the equation has no real solution. Because 5x squared plus 3 is greater than 0 for all x. Okay, for all real x. X. So therefore, now we have to make our statement. It is not possible. Okay, it is not possible for the x-axis to be tangent to f. Cool. That was the worst part of this whole question. Yes, the FRQs can overlap with BC, like AB and BC. The ones that are different, though, 3 of them, is like usually question 2 on BC is parametric or polar. The rate in, rate out, though, like those could be the same. The graph of f prime is usually the same. And then the other one that's the same, graph of f prime, and then there's like, sometimes the differential is the same. It depends on their mood. So, hard to say. All right, here we go. So now some Unit 10 stuff. So Unit 10, they want us to find the second degree Taylor polynomial for f about x equals -1. So for this one, we have to know the formula for Taylor. Okay, a Taylor series uses this formula. It's the series from n equals 0 to infinity of the nth derivative at the center And let me just see how I'm going to do this. You know what? I'll write it and then I'll shrink it. How about that? So it's the nth derivative at the center. So I'll just clean that up a little bit. Times x minus c to the n over n factorial. But if it's a Taylor polynomial, we don't have to go like all the way out here. So this is the packaged and this is the expanded. Like it's like f of c plus f prime c x minus c, and then it's f double prime c x minus c squared over 2 factorial. And this goes on and on all the way. So here, when they tell us second degree Taylor polynomial centered about -1, the degree is 2. So this is up to n equals 2, and the center is -1. So for that part, what I'm doing is first just setting it up. I'm going the second degree Taylor polynomial, and the center, once again, is at -1. So I'm saying f of -1, and then we have plus f prime of -1. The only annoying part here, so f prime -1, the only annoying part, I think, is when you go minus 1, it becomes +1. So just be careful of that. That's like something annoying that could, like, get you. And now that we have the formula, I'll just shrink this all down. Okay, so we have this. I'll put back with this. Like, these are the same formula. This is just packaged up, and this is the expanded. So this at -1 times x plus 1 squared over 2 factorial. All right. So then from here, I'm just going to group this and then shrink it. And I'm going to drag this to the later part of the test because we're going to need this for the last question. If it'll, I'll keep like throwing it down the line. So preview of the later stuff. All right, cool. So we'll need this later at some point. So I'll just leave that there. All right, so here, this is going to get us set up with part C. Okay, so we're just writing the second degree. Now, for this, they told us some of the pieces here. So from earlier, we had f of -1 equals -4. F prime of -1, that's equal to the derivative. Okay, that's dy dx at -1, -4. Okay, because the corresponding y value is relevant here. And we found dy dx at -1, -4 was equal to 6. All right, so we're just going to borrow that again as equal to 6. And now the f double prime of -1, that was equal to, we had the second derivative at -1 is -9. So with these questions, sometimes it's tricky to see that the second derivative, d squared y over dx squared, is going to give us f double. But yeah, we're just using the information from earlier. So now I just plug in, and I have the second degree Taylor is -4. Let me just clean that up, -4. And then we get plus 6 times x plus 1. And then we have -9 times x plus 1 squared over 2 factorial. And you could just leave it like this. You don't have to simplify. If that bothers you, then just say -9/2 x plus 1 squared, but this is fine. Okay, cool. So that's this part. And now I'll shrink this down. And we'll move this because we need to make space for part D, Euler's method. All right, so Euler's method is the last piece. So I'll shrink this, and we'll move this over here. Okay, so this was part C. So now part D, Euler's method. I personally like to make a table for, what's the biggest BC topics? Oh, unit 10 for sure is like pretty massive. Unit 9, I mean, unit 9 and 10 is like really just all BC. I mean, you do have to know improper integrals, like that'll show up. But the the best thing you could look at, honestly, is like the by percents. So yeah, that's yeah, what's happening here? Oh, who do I need to mute? Who's being annoying? Just say the names. Now I gotta read this. Oh, I think I see who. Okay. I think. Hang on, give me a minute. I'll kick some people out if they've been. Hang on. Yeah, I gotta scan back a little bit. Yeah, because I'm just trying to. Let's see. Okay. Cool. All right, so that's one. All right. Let me just see. Sorry, I'm just getting people out who are just here spamming. All right, cool. That's one. Who else? Yeah, sorry, I'm just taking a little pause here to see who is. All right, here's one more. All right. Cool. All right, I got rid of some people. All right, if I gotta get more people out, I will. No, next year I gotta get moderators and stuff. But yeah, please, just a reminder, keep it real in the chat. Yeah, if people can't be nice, I'll just read and then I'll have to decide who and throw you out. So please, yeah, be nice. And if you say harassing things, I press the report button, and then whatever Google decides to do, yeah, that's on you. So yeah, don't say anything too crazy. And now we will move on. Awesome. All right, but if anyone else, like, I'll monitor, then. Okay, so now let's move on here. Yeah, you could leave it as is. You don't have to put in actual values here for the Taylor. You could leave it like this. If you want to just say minus, 9/2 x plus 1 squared, then you could do that. All right, cool. So whichever. They don't take off points for not simplifying in this, no calculator part of the test. So now part D. So we go on. And Euler's method starting at -1, we're going to approximate f of 0. So here, I like to make a table. You don't have to make a table. I just find the table helps you stay organized. And the concept of Euler's method. So if you're like, what is, and let's say I'm starting here at A. And there's my tangent line. And I want to know what the function value is at B. I'm like, oh no, this is not accurate enough. Euler's method is basically like what you learn in Calc AB, the tangent line approximation, but you pick some new value here. Let's say I call this point C. And I plug in to the tangent line to get a y value. And then I also plug into the derivative to find a new slope. The new slope is going to allow our new tangent line to change direction. And notice now that my approximation at B is closer than it would be if I used the red line. So that's Euler's method, the concept. So here, if I look over here, like what we have, I'm starting at -1. And my y value is -4. So then dy dx at -1, -4, we found before was equal to 6. Okay, so this, once again, is the concept. And yeah. All right. So I'll just shrink this and move it over because we'll need the space. So once I find my x, y, and dy dx, then I just write the equation of a tangent line. You could even use the Algebra 1 version, which is this. And from here, I'm going to have y minus -4 becomes y plus 4 equals the slope is 6 times x minus -1 becomes x plus 1. And now we have y equals 6, x plus 1, and then -4. Okay? So now here, we're trying to approximate f of 0, taking 2 steps of equal size. So if I'm going 2 steps to get from -1 to 0, so -1 to 0, and I jump twice, my halfway point is -0.5. So then I have y of -0.5 is 6 times -0.5 plus 1 is 0.5. And then -4. So 3 minus 4 is -1. So that's going to be my y value here. But then what I do with this is I have to find the slope, dy dx, at this point, -0.5, -1. So that's like basically like what's happening over here is I'm plugging the point into the derivative to get my new slope. So my new line gets me closer to the curve. All right. And now we use our derivative from earlier. The derivative from earlier is 5x squared. So I have 5 times x is -0.5, or I can even say -half squared. And then minus 6 over -1 minus 2. Okay, so this is 5 times 1/4. So that's 5 over 4. And then -6 divided by -3 is +2. And now think of that as 8 over 4 plus 5 over 4. And 8 over 4 plus 5 over 4, let me just give a little more space. So this is 5 over 4 plus 8 over 4 is 13 over 4. Okay, so 13 over 4 is our new slope. Now, once we have our new slope, we could write one more tangent line. Okay, so our new tangent line now, we're using this formula again, is now y minus y1 is -1, so I get y plus 1, is now equal to the slope is 13 over 4 times x minus -half is x plus 1/2. And now we plug in 0 to approximate f of 0. So I could finally say f of 0. Actually, you know what? Before I do that, let me solve this for y. So I'll say y equals 13 over 4, x plus a half, and then minus 1. Okay, so f of 0, the final answer here, is we got 13 over 4 times 0 plus a half is a half, and then minus 1. So this makes 13 over 8. Minus 1, I'm going to call 8 over 8. And that's equal to 5 over 8. So 5/8 is our approximation. All right. So moving on. All right, so we go on to parametric time. So we got 3 more FRQs. Yeah, Euler's method, just be careful when you do it all. That's like, the best we could hope for. All right, so part A, we're finding the x-coordinate of the position of the object at time t equals 4. They told us position is x of t, y of t. And one thing to point out is the concept that's big for A is that the integral, well, I'll just say it. The integral of velocity tells you change in position. That's displacement. Okay, so that's just important stuff that we're going to need. So here, if we want to find the position of the object, the x-coordinate of the position at 4, this is just, we're starting off with this. So we're starting off, if I write it in a different color, with x of 2 equals 1. So I could say here that this is equal to x of 2 plus the integral from 2 to 4. We have to be careful here. They made this question a little bit different, not starting us at 0. They started us at 2. So we're going to do this plus x of 2 plus integral 2 to 4 of x prime of t. And x prime of t is the same thing as this. Okay, so I could say, yeah, x prime of t is, this is also x prime. dx dt is equal to x prime. So now we just have to tell the calculator to find this. So I get x of 4 equals, and we have x of 2 is equal to 1 plus integral 2 to 4. And I can leave this abbreviated as x prime, but I'm going to tell the calculator this. Okay, this is what we're telling the calculator. Now, for this part of the test, I recommend that you switch to parametric here. Although they didn't actually define dy dt. See, dy dt is not explicitly given. So actually in this case here, this is a rare case where I'll actually just leave it in function notation. And now I'm going to go to the y equals here. And I'm going to punch in 3 plus cosine of t squared. I'm just going to write x squared. Cool. And now we go back to the main screen. And now I could just write in x of 2 was equal to 1 plus math 9. Now the integral was going from 2 to 4. And dx dt, or x prime, I just saved in the y1 spot. So alpha trace y1. And then we have this. So it's 7.133. Okay, so 7 point x of 4 is 7.133. All right, cool. So all right, now let's move on to the next part here. How many FRQs on the real test? Just 6. Yeah, so just 6. All right, so part B. Now we have at time t equals 2, the value of dy dt is -7. So write an equation for the line tangent to the curve at this point. All right, so at t equals 2, So t equals 2 gives us this. Tells us we have the 0.18. So far, like, this is like something useful. But if we want to know what is the slope of the tangent line, that's y prime of t over x prime of t. Right? Some people might remember it as dy dt over dx dt. Okay, like this is also it. But we can express it this way. I like to write it this way because when we plug in 2, the notation is just easier to write. Like dy dx at t equals 2. Then I could just say is y prime 2 over x prime 2. So this is y prime 2 over x prime 2. And y prime of 2, they're telling us, like if at t equals 2, dy dt is -7, they're telling us here that y prime of 2 is -7. So now I just, type all that in. All right. So alpha y equals enter. We have y prime 2, we just said is -7. Over x prime 2, I saved x prime in the y1 spot. So I press alpha trace y1, and we're evaluating it specifically at 2. And we get this. We get -2.983. Okay, so -2.983. I'll leave this one here because just in case, people want to keep track of what I just typed in. So this is how it'll simplify. Yeah, if you get that 108, that's you'll be famous forever. Each year though, there's like, I don't know, like less than 10 people that get a perfect score on BC. It's like not that popular. There was like one year that like only one kid got it. So yeah, maybe it's one of you. Who knows? Okay. So this is, I shouldn't box it off. That's not our answer. That's going to get us to our answer. So now that we have this, we're going to write the equation of the line tangent. So this is our point, and this is our slope. So then we'll have y minus 8 equals -2.983 times x minus 1. All right, that's it. That's what we got to do for B. Part C, find the speed of the object at time t equals 2. So speed is, just in general, for parametric, speed equals x prime t squared plus y prime t squared. Okay, so this is the formula to know. So at t equals 2, I'm just finding x prime of 2 squared plus, and remember they told us that dy dt at 2 is equal to -7. So I could say plus y prime of 2 squared, but this is just -7 squared. Okay, but if we want to just say y prime 2 squared and do the rest in the calculator, that's also okay. All right, this, is -7, but I could just write it like this and then do the rest in the calculator. So I have square root of alpha trace y1. Actually, let me do parentheses first. Parentheses y1 of 2 squared plus, please make sure you write -7 in parentheses before you square it, or just write 49. And you get 7.383 if we round to 3 places. 7.383. So this is 7.383. Yeah, the equation of the tangent line, we don't actually have to write it y equals mx plus b. You could leave it, in this expanded, this form over here, in the point slope form. Because it's not worth the risk of losing a point. If you do the algebra wrong, and that's not even part of like your actual grade, it's like so devastating to lose a point for that. So that's why I just tell my students, like, nah, like, don't even bother. All right. So now this part here, they told us the line tangent to the curve, x of t, y of t, has a slope of 2t plus 1. And we need to find the acceleration vector of the object at time t equals 4. Okay, so if they're telling us the line tangent to the curve has a slope of 2t plus 1, then what they are telling us here, remember, dy dx, I could say is equal to, did I leave it up here? Oh, I think I erased it before. But is dy dt over dx dt, or I could say y prime of t over x prime of t. But a few things here, they're telling us that the line tangent to the curve has a slope of this. So for t greater than or equal to 3, this is happening. So they're telling us, like, that's dy dx. Okay. So I'll just say here that for t greater than or equal to 3, based on what they told us, dy dx, I'm going to set equal to 2t plus 1, and saying this is equal to y prime over x prime is the same thing as dx dt, which is 3 plus cosine of t squared. All right, and now our goal here is to find the acceleration vector of the object at time t equals 4. So for the acceleration vector, I have to know the x and y acceleration. So this abstract idea is going to help us find the y acceleration. So here I just do a little bit of algebra, and this tells us here that y prime of t in this time frame here is going to be 2t plus 1. And let me make that a little neater. So 2t. Let me just try that again. I'm going to write my t as a script, because when it's like t and then plus, it just could look sloppy. So 2t plus 1, and then 3 plus cosine of t squared. Okay, so then if I want to find the acceleration at t equals 4, I could find x double prime of 4 first. X double prime of 4. So now I'll open up the calculator here. I saved x prime here. So x double prime would be the derivative of x prime. So the derivative of alpha trace y1 of x prime at 4. And I get this value here. Now for the next piece, I'm doing math 8, the derivative of y prime. So I'm going to write in that whole mess. So 2x plus 1 in parentheses. And then in the next parenthesis, I have 3 plus cosine of x squared. And this is at x equals 4. Gives us this. Okay, so these are the values that we're going to need. Is that? Oh, cool. That goes over that one. And let me just crop this. Okay. So then from here, what we're going to do is just record the results. So x double prime of 4 is 2.303. And now y double prime 4, they know that you could just use the calculator for this, is 24.814. If you stop here, this is a sad way to lose out. They said to find the acceleration vector. Okay, so we have to write it as a vector. So we could just say here that a of 4, the acceleration vector at 4, I'll write, vector valued over here is comma separated. And there it is. Okay. Cool. Alrighty. So moving on to the next phase. And well, once again, just thank you to everybody who's here. Yeah, overall, I'm just like like we're 2 hours and 30 minutes in. There's like 1,500 of you almost that stopped by, and just yeah, thank you for that. You all being a part of this and like making this review special. Yeah, it's like just mind blowing that like I'm able to teach to this many people at once. Thank you for being a part of it. And if you haven't subscribed yet and this review is helpful, I would appreciate you subscribing and let your classmates know. But the word is traveling. I think yeah, like each year the streams seem to be growing. So yeah, thank you all though for like being a part of this. It does mean a lot, like knowing that this is going far and that you're all getting something out of this. The comments, the chat, I appreciate it. And yeah, so just thank you all. And we have, what is it, 2 to go? Is it? Wow, the final 2. Okay, so let's do this. Find the area bounded by the curve and the x-axis. So here they gave us the interval from 0 to pi. And the formula for polar area is this. Okay, so this is the formula to know. Now, the concept I like to use is windshield wiper motion. So when we are thinking of a polar region, I mean, I can even just use this. Like if I want to talk about this area, let's say here, theta 1 to theta 2, I just think of like a windshield wiper going like this. Oh, William, thank you so much for the tip. I do, yeah, I appreciate it so much. Thank you, William. That was very kind, helping me out here. So when we want to come up with the limits, I think of like circular motion. So I just imagine kind of like when a windshield wiper cleans your windshield. It's like the angle, like the part of the windshield that the windshield wiper cleans is like the polar area we're looking for. Except our polar function, it's like a magic windshield wiper that as it swipes, the length of the windshield wiper like retracts and goes back out. So it's a hard concept to really master. But yeah. All right. So here they told us the limits are going, we're going from 0 to pi. We do get a calculator for this. So this is something like, let's hop over to the calculator and switch it to polar mode. And now I'm going to go to the y equals, and I'm going to type in 1 plus, actually, no, I lied. I'm going to type in r is theta plus sine 2 theta. Now, when I graph this, I'm only going from 0 to pi. So I'm just going to make theta max go to pi. And then everything else, x minimum, let me just see. It goes, I'm going to go from like -5 to 5. Because on the graph they gave us, it goes like -3 to 1. So I'll just go a little bit out more. And then for the y, I'll go, let's say -1 up to 5. And now I press graph. And maybe here I could lower the y maximum, lower it down to 3, just so we get a nicer picture. That's a better picture. And it matches the one they gave us. So the reason I mean, the reason I want to write this in is that now I could see here that the values for r are positive. And I know this because they drew it out for us and they said we're going from 0 to pi, and the graph is in quadrants 1 and 2. So it's not going to like flip and go the opposite way, but that's something that, I just wanted to mention. So we're going to have 1/2 integral 0 to pi of the function theta plus sine 2 theta. And this is being squared. Okay, and then d theta. So that is what we're going to find. We save that in the calculator as r. So now I just go back to the main screen. 0.5, math 9, 0 to pi. And then r is alpha trace r1. I like to save it just in case I have to write it more than once. And there it is, 4.382. Okay, so this is 4.382. All right. This next part is a little annoying, but the formula for this part is you have to know that x is equal to r cosine theta and that y is equal to r sine theta. Okay? So here, if they want us to find the angle theta that corresponds to the point on the curve with x coordinate -2, look, when x is -2, that's this point over here. That's the, like, so we're looking for, like, what's the angle? Like, what's the measure of this angle here? Okay, like, how much are we going, like, from here to here? So theta equals, like, what is that? Okay, like, that's what the question is asking us to find. So now let's go ahead and find it. So here, if the x coordinate is -2, I'm using this formula. And let's go, I'll write this in blue. So x is -2, so I have -2 equals, instead of r cosine theta, r in this case they define for us is this. Is theta plus sine 2 theta. So theta plus sine 2 theta. So what makes this question a little tricky is, like, we have to be really good with the calculator. Now I'm going to switch back to function. And I'm going to solve this equation in the calculator. I'm going to go -2. And then on this side, I'm going to do parentheses x plus sine 2x, close, close, and then cosine x. And now window, the x is going from 0 to pi. That was the domain they gave us. And now for the y, we want to know, when is this equal to -2? So I'm going to go to like -5 and 0. Because y equals -2 is here, and there's the intersection. So second trace 5. Remember, when you're in the calculator section, just make sure you're not solving crazy algebra equations by hand. Please make sure you use the calculator. Okay, so we're going to get 2.786. Okay, so 2.786. So this tells us theta equals 2.786. So if I were to, like, let's say, just explore that a little bit more. So let's say here I go second mode, second answer, and I store this as my new A. And now I go back to polar. All my stuff is going to be saved. At least I hope. Oh, it's not. That was a tragedy. All right, 0 to pi. And now -5 to 5. I mean, it's a necessary thing. We do have to get the solutions. I think I went -1 to 3. Right, so there's our graph. Second trace value. And let's say I type in A. And you see that gives us an x value of -2. So this is definitely good. All right, cool. Wait, don't understand how. Oh yeah, they're asking when x, when is the x coordinate -2? So I plugged in x is -2. So let me just highlight this. I plugged in x is -2, and then r is equal to this. Okay, so that's what happened. Like, r is this, x is this. Alrighty? So that's how it's working. Cool. So then, now for part C. This part was a little tricky. And the rubric, I actually didn't agree with everything they said, only because there was like one detail I think they could have been more careful with. For pi over 3 to 2 pi over 3, drd theta is negative. What does this say about r? And what does this fact say about the curve? But one thing you have to be careful of, if drd theta is negative, that means r is decreasing. But it doesn't always mean that the curve is moving towards the origin. You could have a situation where r is negative. If r is less than 0 and drd theta is less than 0, like if this and this is true, then, so I'll say this, like, yeah, if, make that neater. So if this, oh yeah, if r less than 0 and this, then the curve goes, so then the curve goes away from 0, 0. Okay. Because people will say like, oh, dr d theta is negative. R is decreasing. It's moving towards the origin. If it's negative, it's still going to, like, if R is negative and dr d theta is negative, it's going to move away from the origin. So just be careful of that. This is like a sneaky, sneaky detail. They had a question like this on AP Classroom too. And it definitely tagged a lot of people. So dr d theta is less than 0. Then tells us, so implies that R is decreasing. Okay. And that doesn't matter if like R is positive or negative. It does tell us R is decreasing. But what does this say about the curve for the next part? Well, if, oh, and let me just mention, since dr d theta is less than 0, I'll just say on pi over 3, 2 pi over 3. So I'll be specific. Pi over 3, 2 pi over 3. Then R is decreasing on pi over 3, 2 pi over 3. All right, precision is good. You want to be precise, especially if like you're building a bridge. Okay. So here, for the next part, since I'm just going to say R is greater than 0 on pi over 3, 2 pi over 3, this is, I personally want to mention this. Since R is greater than 0 on this interval, and dr d theta is less than 0 on the interval, the curve is moving towards the origin. Okay, which you could kind of see here, like pi over 3 is like here, and then let's say it's like over here, that, see how like this is the radius, and then like moments later, the radius is shrinking, the curve is getting closer to 0, 0. See, like it's moving towards the origin. Okay, that's the concept. But that's only possible here because R and dr d theta have opposite signs. So R is greater than 0 on this interval, and dr d theta is less than 0 on the interval. Therefore, the curve is moving towards the origin. All right. Cool. And now I'm going to shrink this, and we'll do the last part, part D. And then after this, we move on to the final question. So we're making good progress. All right. I think I would have finished this like in just 3 hours if I didn't have to send those trolls packing. So let's move on here. So part D. Find the value of theta from 0 to pi over 2 that corresponds to the point on the curve in the first quadrant with greatest distance from the origin. Okay, so greatest distance from the origin is like here in this neighborhood. Okay, so whatever that point is. But what we're going to do is unit 5 concept. If we want to know when R is the greatest, okay, the absolute value of R is greatest, but R is positive on this space. So we're really just looking for when R is the greatest, like greater than 0. So we're going to look for when is dr d theta equal to 0. And dr d theta equals 0 when this equation is equal to 0. And that's something that I could use the calculator for. But I'm going to pretend this is no calculator. Let's say I have to solve 1 plus 2 cosine 2 theta equals 0. Okay, this is going to give me cosine 2 theta equals, I do minus 1, and then I divide by the coefficient 2. So now we remember this, ASTC. If cosine is negative tells us that we are in quadrants 2 and 3. Now you might be saying, wait a minute, we're in quadrant 1, but it's 2 theta. So when we solve for theta, it's going to put us back in quadrant 1 anyway. So that tells us, like, if we're restricted to quadrant 1, we don't want to go all the way here to quadrant 3. We're going to go to quadrant 2. So then the next thing I think of is like, oh, cosine of 60 degrees or pi over 3 radians is a half. So then that tells me here that if I'm in quadrant 2, I would have cosine of 2 pi over 3. And that would give us negative half. Okay, because my reference angle, this is my reference angle, pi over 3. So if I go pi over 3 this way, from standard position, like just think here, let me make that a little more accurate. So pi over 3 this way would be like this. Then this would be 60 degrees. It would be 120 degrees. That would be 2 pi over 3. Okay, so that tells us here that 2 theta. So then this implies that 2 theta is 2 pi over 3. Which then implies that theta is pi over 3. All right, and did I group all this? I did. Let me shrink this down. Only because we're going to need that space. Right, that's all connected. If I do that. Okay. So I'll just group this and give us some space to close this out. But look, you could just trace this in the calculator, right? You don't have to do this by hand. You can write the decimal value. All right, so now I'm going to make a table. We're in quadrant 1. So I have 0 and pi over 2 are my endpoints. But then I could plug in pi over 3. All right, and if I plug in here, r at 0 is just 0. If I plug in pi over 2, I'm going to get pi over 2 plus sine of pi is 0, so pi over 2. But look, from here, I can just go to the calculator, go here. And remember, I put the calculator second window in ask mode, so I could just type this stuff in. I could even just say, like, yeah, 0 gave me 0, pi over 3, and pi over 2. Right? If you just want to type the derivative in, you know, like type in drd theta and set it equal to 0 and trace, you can also just trace. If you're like, hey, I don't want to do trig by hand, then just go to function and I'm going to type in our derivative here. Our derivative is 1 plus 2 cosine 2 theta. And we are going from 0 to pi. Okay, so from 0 to pi. And if I graph it, you could see, oh, I'm sorry, pi over 2. We're in quadrant 1. So I don't even have to go that far. I could go, we're in quadrant 1. And you see this is the point. Second, trace 0. I just trace the root. Enter, enter is this. Okay, and that number, if I double check it, is equal to pi over 3. Okay, so I didn't even have to do that myself. I was just, once again, showing you, like, that's how you would get there if you wanted to do that. You don't have to know the root test. That's not on the poster, so yeah. If you do know something, though, I don't, you know, can an endpoint be a critical point? I mean, yeah, the max can happen at the endpoint. So when you're looking for an absolute max, it's possible. What's nice about this, though, is you have a graph in front of you. Like, honestly, if you just look at all this, all right, and you say, all right, I'm going to look here and say 0. So at 0, I'm here. At 60 degrees, I'm here. And at pi over 2, I'm here. I'm like, all right, it's definitely 60 degrees. You know, like, you could use the graph to your advantage. Like, common sense will get you a long way. But that's the sharpening the axe thing I was talking about before, which is hard to do when you're in the middle of an AP test and you're tired. Like, sometimes you just miss it, you know. So here, these are the values. And if I just want to copy these values down, you know, I could just copy those values down and it's fine. So I could just say, you know, I don't have to know, like, how to do radians and all that fun stuff. And, you know, plug in and simplify. I could say, all right, 1.913. I could say 1 point and then 571. Okay, so I could just do this here. And now the question, find the value of theta in the interval that corresponds. So we could just say here at The point on the curve in the first quadrant with greatest distance from the origin occurs at theta equals pi over 3. Okay, so we could say the point with the greatest distance. So with the, and let me get rid of this now that we don't need this anymore. So the point with the greatest distance from the origin in quadrant 1 occurs at theta equals pi over 3. Okay, the justification is this table here. All right, that's more than enough. It's if you have a closed interval, then you check the endpoints. Okay, just look up the extreme value theorem. So I would just look this up. Extreme value theorem. Extreme value theorem says as long as you have a continuous function on a closed interval, then the absolute maximum or absolute minimum is either going to occur at a critical point or an endpoint. So yeah, extreme value theorem. Yeah, you could just look that up, honestly, even on Wikipedia. F must attain a maximum and minimum at least once, okay? And it's going to occur at either a critical point or an endpoint. So that's, yeah, just look up EVT. Final boss. And there's the formula I said we would need. So here, this was a hard question, I thought. Like the last part is kind of mean because of this. This was the evil detail I'm going to highlight. We have f is a function with derivatives of all orders. We have this, but when n is odd, the nth, so this part, when n is odd, the nth derivative of f at 0, when n is odd, the nth derivative of f at x equals 2 is 0. And when n is even, and n is greater than or equal to 2, the derivative of f at x equals 2 is given by this. And the first thing we have to do for A is write the 6th-degree Taylor polynomial for f about x equals 2. So you could say 2 or, you could say p or t. I'll just say polynomial like this. But if you want to say like the Taylor polynomial, we could call it capital T. We could just say capital T sub 6 of x. But this is the part that might throw people off. When n is odd, the nth derivative is 0. So that's talking about like f prime, f triple prime, f fifth prime here, and so on. Like the odd primes, the derivatives here are all 0. Okay, like these all equal 0. So that's what this is saying here. That's like a little abstract. So that means when I write this out and I use this formula from before, my center is at 2, is that I'm starting this with f of 2. But I'm not going to write this because f prime is 0. So like this piece just wipes out. But then my next non-zero piece is f double prime of 2 times, I'm centered at 2, so I have x minus 2 squared over 2 factorial. Okay, and I'm just going to use this the whole way through. So let's go ahead and do that. So I have this. Then I have my next even one. So my even power. I have the 4th derivative at 2. X minus 2 to the 4 over 4 factorial. And now we have one more. The 6th derivative at 2 times x minus 2 to the 6 over 6 factorial. Okay, so this is all of them. Now we go on a scavenger hunt. F of 2 is not a challenging scavenger hunt, it's just 7. But now for this is where we have to just start plugging in. So now I have when n equals 2, this is going to tell me my second derivative at 2. You don't have to write like 2 like this. You can if you want. I would rather write f double prime just because it looks familiar for how we usually write it. So n equals 2 is going to give me 2 minus 1 factorial over 3 to the n, and n equals 2. If you don't want to risk it, don't simplify it. Leave it like this. although that looks messy. This is going to make 1 over 9. Okay. And then the next one I would say we need to know here is when n is equal to 4, f double prime of, I'm sorry, let's start that sentence over. So we're plugging in n equals 4. So we have the fourth derivative at 2 is equal to n minus 1. So I have 4 minus 1 factorial over 3 to the 4th power. And now this is going to make 3 factorial. 3 factorial is 3 times 2 times 1. And this is over 3 to the 4th power is 81. But this part here, like, honestly, it's like not a lot of value here to simplify. So I'm going to leave this. I'll leave it like this. Okay, I'm just going to write 3 factorial over 3 to the 4th. And then for the 6, n equals 6, I'm going to write, I guess I'll just keep writing it underneath. So n equals 6 is going to give me the 6th derivative at 2 is 6 minus 1 factorial over 3 to the 6th power. Yeah, that's why, like, this is just not worth, like, finding 3 to the 6th power. So just got tired of, writing all that. So we'll stop it there. And now we have to plug in to get our polynomial. Oh, I should mention, this is 3. This is 1. This is 5. The last question, I didn't write the point spread, but it was 3 and then 2, 2, 2. Okay. And did I write the one before it? I did not. So the one before it was 3, 2, 1, 3. Okay, so that was, the point spread there. But the rubrics are online if you want to look it up. Alrighty, so now I plug into this. T sub 6 of x is equal to f of 2 is 7. So I have 7 plus, and just make sure I'm on the right page just to keep track of what I'm doing. And then I have plus f double prime. I could write as 1 over 9, but you know what? I'm going to write it as this part here. I'll just write it as 1 over 3 squared. So 1 over 3 squared was the unsimplified. And then I have x minus 2 squared over 2 factorial. And then for the fourth derivative at 2, we had 3 factorial. Let me just write that a little higher. 3 factorial over 3 to the 4. And then we have x minus 2 to the 4 over 4 factorial. Okay. Oh, let me just. Yeah, I mean, graphing the original. So these are all like viable options like that you could go with here. Oh, and at Norja, 6th degree just means the highest power of x. So when I hear the degree, 6th degree, let me just maybe do that in pink. So 6th degree tells me to stop at 6. It doesn't necessarily mean I have 6 terms. Okay, so if I'm understanding the question correctly, that's something to. All right, so now moving on here, let me just make sure 3 factorial over 3 to the 4. That's this. And then x minus 2 to the 4 over 4 factorial. And then finally, for the 6th derivative at 2, it's 5 factorial over 3 to the 6 times x minus 2 to the 6 over 6 factorial. Okay, so this would get us the full credit for A. Right, so this is our, it's a mess, but it is our polynomial. That's 3 points. All of that for 3 points. I mean, I guess it's just like, it's really just like all algebra. All right, and I heard that a while back, but I really, agree and think Calc 1 and Calc 2 is like really like 70 to 80% algebra. Just like you have a formula and you're plugging in. So just, know your formulas and you'll be fine. So here in the Taylor series for f about x equals 2, what is the coefficient of x minus 2 to the 2n? Okay. So one thing to pay attention to here, because this one is definitely like where things start to get abstract, is I want you to think about the relationship between the power of x minus 2 and the derivative we're up to. So x minus 2 squared, second derivative. X minus 2 to the 6, sixth derivative at 2. So here, for part B, what you want to think about is if you're looking for the coefficient of this, you could see that it's going to be the 2n derivative at 2 times x minus 2 to the 2n over 2n factorial. Okay, so this is what we're looking for. So this is 1 point, but this I thought is where things start to get tough. That was like not an easy find, but the key was looking at the relationship between the power of x minus 2 and the derivative that we're looking at in terms of the formula they gave us. So this piece is the one we have to be the most careful with. So now, side quest. Okay, we go on a side quest. The 2n derivative at 2 is equal to, and now I just plug in, I have 2n minus 1 factorial. So you see, instead of n here and here, I'm replacing it with 2n. So I have 2n minus 1 factorial over 3 to the 2n power. So from here, now I plug this in over here. Like this stuff is what's going to be plugged in over here. So now we're going to have 2n minus 1 factorial over 3 to the 2n power. And now I have x minus 2 to the 2n over 2n factorial. Now, one thing I want to point out is that 2n factorial is equal to 2n times 2n minus 1 times all the way down to like 3 times 2 times 1. Okay, and this I could call 2n times 2n minus 1 factorial. This is a nice little trick to know, because when I write in the next line here 2n factorial, I prefer to write it as 2n times 2n minus 1 factorial, because these terms cancel out completely. And that just makes things simplify much nicer here. Okay, so this is where, like I said, the algebra is going to get a little funky. So now we're going to have 1 over 3 to the 2n and then times 2n. Okay, so we're basically multiplying these two by x minus 2 to the 2n. So this is how it's simplifying. So here, what is the coefficient? I could say, so the coefficient, let me just make that neater. So the coefficient of x minus 2 to the 2n for n greater than or equal to 1 is, and then I could just say 1 over 3 to the 2n times 2n. Okay, so that's the piece we need. Yeah, you don't have to cross it out. The only reason why I want to cross it out is because when we get to part C and we have to find the interval of convergence, it's going to be a mess if it's unsimplified. So, because we're going to have to use the ratio test for the last part. Okay, so I'm just going to shrink this down. And then if we need it, you know, we'll refer to this. All right, now this is the part, final part here. So we made it. Yeah, this one is definitely a little weird. That's why I chose it, just in case they like overcook Unit 10 this year. I wanted to pick something a little wacky. All right, but yeah. All right, so here we're going to find the interval of convergence of the Taylor series for f about x equals 2. So part B was just basically building us up to answer this part. So now what I want to say is, remember, they told us that this is for n greater than or equal to 1. The problem is that if n is greater than or equal to 1, I cannot account for this f of 2p. So if I need to write a function f of x as a Taylor series centered at 2, if I'm not careful and I just say this, so let's say I go from n equals 1 to infinity, and now I write everything that we just wrote here, x minus 2 to the 2n over 3 to the 2n times 2n. So me writing this, if I'm not careful, I want us to think about what I had over here. At n equals 1, just n equals 1 gives me x minus 2 to the second over 3 squared. And then we also have times 2. So do you see how this gives us, where is it? It gives us this term, but it leaves out the 7. The 7 doesn't pop up. So here, this is a little abstract, but the way we fix it, it's like, oh no, what about 7? 7 was left out. We just write 7 plus. Okay, so now the problem is fixed. Okay, so the problem is fixed. That's where you have to sharpen the axe. You have to make sure the series you write down is good to go. So now this, we're going to say here, is our a sub n. So a sub n is equal to x minus 2 to the 2n over 3 to the 2n times 2n is the base. Well, at the base. It's like not the base of the exponent. So now interval of convergence tells us to use the ratio test. So we're going to do the limit as n goes to infinity of absolute value. I have to do a sub n plus 1. Okay, so a sub n plus 1 is x minus 2 to the 2n plus 1. So this one was really rough because I had to distribute also. Yeah, this one's like really just not polite at all. Okay, and then times 2 times n plus 1. And remember, the ratio test calls for us to do this divided by this. So here's what I'm writing here, and you have to write this at the AP test. That's a sub n plus 1, that piece. When I divide by a sub n, when I take the ratio, I could just flip the whole thing. I could just say keep change flip and say times 3 to the 2n times 2n over x minus 2 to the 2n. Okay, so now we will simplify this. So now the fun part, the algebra. So here, the limit as, let me just change to a completely different color. So the limit as n goes to infinity of, and now for this part, I have x minus 2, so x minus 2 to the 2n plus 2 over 3 to the 2n plus 2 times 2n plus 2 times 3 to the 2n times 2n over x minus 2 to the 2n. Okay, so from here, now we cancel. So x minus 2 to the 2n versus this. You see how like 2n plus 2 is 2 more than 2n. So when this cancels, this just becomes a x minus 2 squared. This one versus this one, 2n versus 2n plus 2, this one wins by 2. So this one's out, and this becomes a power 2. So now, simplified a little bit more, this is the limit as, make that neater. So limit as n goes to infinity of x minus 2 squared. So x minus 2 squared over 3 squared times, and then I'm left with 2n over 2n plus 2. Be mindful here that the limit is as n goes to infinity, which tells us to focus on the leading terms with n's, and that limit is going to 1. So then this is the absolute value of x minus 2 squared over 9. So we get here, one thing to point out, small detail, is that x minus 2 squared is greater than or equal to 0 for all x. So from here, I could just get rid of the absolute value completely and say that I want, so what do we want here? We want x minus 2 squared over 9 to be less than 1. And now more algebra. We want x minus 2 squared. Clean that up. So x minus 2 squared to be less than 9. So from here, we could say a few ways to handle it from here. I mean, we can say that the center of our series is 2 and the radius of convergence. Yeah. But this, honestly, from here, I would rather just deal with this algebraically. So a quadratic inequality, here's another piece, is I just pretend here that when I get to the x minus 2 squared step is less than 9, I imagine what this looks like. X minus 2 squared, make that neater, is a parabola. Okay, and 9 is up here. So I just think about, like, if this were an equation, x minus 2 squared equals 9, would tell me if I square root both sides, that x minus 2 is equal to plus or minus 3. And then I just think about, okay, like these two, like this is just kind of like the math that I'm working out. You could even use a calculator for this, like x minus 2 squared equals 9. You have this, but you also have this. So the values here would be x equals 5 and x equals, if I do plus 2, I get negative 1. So basically this part here, then I could just jump right to saying, oh, negative 1 is less than x and is less than 5. It's like solving a quadratic inequality, which is like kind of like a heavy pre-calc topic. But I just pretend that it's an equation, and then I see that it's less than 9 between the roots, okay, between the intersections here. So yeah, this one was like particularly not pleasant. That's why I chose it, because it looked horrible. All right. So here, now we're not done. We have to check. This is the interior interval of convergence. So now I check, let's say x equals negative 1. I have to check the endpoints. And then this is the last thing we do. So if I check x equals negative 1, all right, what this is going to give us is we're going to have 7 plus sigma n equals 1 to infinity. And I have 1 minus 2. I'm sorry, negative 1. Negative 1 minus 2 is negative 3 to the 2n over 3 to the 2n. And then I get 2n down here. All right. So for this one, what I could say here is, now I'm just going to do this algebra also on the side. Negative 3 to the 2n is the same thing as negative 3 squared to the n over 3 squared to the n. So this is going to become 9 to the n over 9 to the n. So that's why, like, these just cancel out. So then this becomes 7 plus 1/2. Like, I'm just bringing out the 2. Okay, and then 1 over n. And now if we comment on this, I'll get rid of this now. That's just like our side algebra. I do that math like in my head, but like that's like kind of like annoying math to do in your head. It's like not the most pleasant. But this, I could say, diverges because just this piece alone. Whoops, I should actually write the 1 over n. Diverges. That's the harmonic series. And now I check the other endpoint. If I plug in x equals 5, I'm going to get 7 plus sigma n equals 1 to infinity. And this time around, if I plug in, I'm doing 5 minus 2 is 3. to the 2n over 3 to the 2n times 2n. And it's the same exact argument. Okay, so this cancels out, and it's equal to 7 plus the integral from n equals 1 to infinity of 1. I'll write it in front like this, 1/2 1 over n. And this diverges. Same reason as above. Same reason as the x equals -1. Okay. So now that tells us if it diverges at both endpoints, therefore, the interval of convergence is -1, 5. The endpoints are not included. All right, that was tough. Somehow we made it. 3 hours and 15 minutes. So, yeah, that was true words of Abraham Lincoln, definitely. How long will this live stream be for? I mean, I'm basically done, but I mean, I'll stay and chat for a minute. I have like an odd amount of energy. Not another hour, probably another 5-10 minutes. Yeah, it's 11:15. But really, thank you all for being a part of this. 2,000, almost 2,000 people stopped by here. This is finished for today. Tomorrow I'm doing this at 3:30 p.m. Eastern time. That's 12:30 on the West Coast. So, oh, you just got here and you're cooked. I'm sorry, Joel Rivera. Just keep studying, and then remember, you will become the chef, and you will do the cooking. Okay, so Joel, my prediction for Monday is, let's see. Whoops. What's going on with this? Oh no, my computer's freaking out. Why is it not? Oh, here we go. So Joel, Monday, here. This will be Joel on Monday. All right. Predictions. Tomorrow I'm going to do like more multiple choice. I don't know. Free response took a lot out of me. You know why? I got to give a shout out to another YouTuber. Like I've never like formally like talked to the guy, but Turk's Vids. That guy does such an awesome job of getting all the FRQs out there. Him and a few others, but like he just stands out. And I tell my students at school, I say like, yeah, watch him for FRQs. Like he breaks them down so quickly and nicely. That yeah, like I almost like stop making FRQ videos because I'm just like, yeah, like he already does them. So like, why am I gonna make the same thing as that guy? You know, like he does a great job at it. So, I'm gonna do some. I mean, that doesn't mean I shouldn't talk about FRQs. Like we have different brains and we're gonna look at it different. But he's really good. He knows his stuff, and yeah, I do like his videos. So, but yeah, ask away. Questions. And let me just see here. Oh yeah, and also if you're here and you have not subscribed, I would appreciate you helping me grow the channel. This time of year is always like just really like very busy for the channel. So yeah, I just I appreciate though, yeah, any support that I could get. So let's see in the chat other questions. What's my favorite chess opening? Ooh, all right. I could talk chess for a second. I like the King's Gambit. It's very aggressive. It's that's why this pen was making my mouse go crazy. I like the King's Gambit. It's a aggressive opening. So wait, now I can make myself more jumbo because if it's Q&A time, I don't need to shrink myself in the chat. But yeah, King's Gambit all the way. Yeah, yeah. I gotta look up if you ask me to say something and it's like off brand with what I'm trying to put out there. I have to look it up first to make sure it's okay. It's not like I'm like supporting. I used to play video games before I had kids. I liked open world games. I played Call of Duty shortly, like for a little while, but it was like too intense. It was I don't know, very hectic, just very like it's designed to make you want to keep playing forever. So I liked open world games because it was like more relaxing and like calmer pace. Like you could kind of dictate the speed. It wasn't like you're respawning and you get like 5 grenades coming at you. So yeah. Um you like to open with right hook to throw off your opponent. Oh, all right, a right hook. You just no, I mean that's against the rules. You just don't like yeah, crack your chess opponent. That would be yeah. Oh yeah, you don't have to do the test questions in order. That's for sure. So yeah, all right. Any other questions here? Polar area intervals. Yeah, for that one, polar area intervals. Let me see. I have it here. This helps. I just like stare at this for a little bit. The windshield wiper concept is big. Okay. So just no, I mean I say stay in a car and just watch the windshield wiper. No, I mean the intervals, it's just like, yeah, the circular motion. So I just imagine like kind of like the windshield wiper, like as it's going, like if I'm here, like I just see like, all right, the angle that it's making, like as it swipes. So like, let's say it's like, if I'm just talking about like this section here, like maybe that's just 0 to pi/4. So like that's how the area is highlighted. Like it goes circular and swipes. Okay, like that's how I see it. Yeah, Barron's is like no joke. I that's why I like Barron's questions. Yeah, the clip. You know, I like playing these silly videos because it's all about having like a good image in your head, like what's going on, and yeah, that's What are my tips to improve your multiple choice? I'm gonna quote one of my students from class of like 2018, 19ish, 18. I think he graduated. He was like one of my top students in the whole school. He got fives on everything, highest grades possible, like in the whole school on all his regions, SAT math 800. And I remember asking him, like, all right, what's your secret? How do you ace everything? And he said that when he practices multiple choice, that he looks at the wrong answers and he's able to say why the wrong stuff is wrong. So if you're getting stuff wrong in the multiple choice, sometimes you just say 5 plus 5 is 12 and whoops, that happens to be an answer. I mean, that'll just happen. Other times, like if you just don't know the theorem, then you got to go back and learn the thing you're missing. But you know, I would find that most of the time it's like students will just go way too fast. They don't sharpen the axe. If you didn't hear that analogy before, if you have 6 hours to chop down a tree, spend 4 hours sharpening the axe. Like really try to get what the question is asking, and like you know your concepts, like you're showing up with all your theorems and your definitions and your formulas ready. Then it's really just a matter about carefully choosing, and before you move on, you're like, did I definitely answer this? And I mean, don't time is also money. Like you don't want to spend every question like, all right, let me look at every wrong answer. And then like an hour goes by and you're like on question 8 out of 30. Like that would stink. So you got to move a little bit, but also, yeah, like I would say, oh, just practice, but change up how you approach multiple choice questions. Like look at the wrong answers and say why they're wrong. And that way, when you take the AP test, you could anticipate the traps that they're going to set for you before you even enter the question. Okay. Like I know when I'm doing like one of those initial value questions, like if I go back to, the stuff we were looking at before, something like here, something like part A. If I look here, a common mistake is that students leave this out. Like, so the trap is that students just go, oh, x of 4 is just equal to this. You know, and they only look at this. They forget to do x of 2 plus. They leave out the initial condition. They leave that out. And if they leave that out, x of 2 is equal to 1, then they're going to have this answer choice waiting. And they're like, great, I did it right. My answer's there. And it's like, whoops, I got it wrong. And like, that's what makes the multiple choice hard, is like the wrong answers are not random. Not like, all right, that's the answer. And like, this is like choice A. And like choice B is like, all right, let me just make up an answer. Like, this, and then this. And then like choice D is like, you know, like, oh, this plus pi. It's like, yay, like it's probably that one. I'm close enough. Like, no, they designed the wrong answers to be like tempting you to do every silly thing you could do. So if you have like a bad idea, like the answer is waiting for you and you're like instant gratification, like, cool, it's there, it must be right. So just, they set traps on every question. College board. No, I mean, College Board at the end of the day has to make a product that people will consume. So if they all of a sudden, like let's say 2025, they made the AP test 5 times more challenging, and let's say the passing rate went from like, I don't know, 70%, 60, 70% down to like 5% or something crazy, then no one would take the class anymore, and then they would lose all the money. So there's no incentive for them to overcook the test to the point where no one can do it. So it'll always be fair and within reason, because it is a business at the end of the day. So yeah, that's my take. Anyone else? I'm glad there's 80 of you still here, just here to chat. Other questions? So MCQs, watch out for traps. Anticipate the traps. Terrible at polar. Yeah, a lot of people don't like polar. It takes time. I would say the foundation and trig is big. I mean, I don't know. This might be a radical thing to say, but I think like it's possible to really skip pre-calc and go right to AP calculus if your algebra is like really strong, because like the trig stuff, if you learned it in geometry, is like, yeah, I mean, I guess it is a little, it does help to have pre-calc for sure. But if you're really motivated from September, like you could bypass like not having it. It's totally possible. I've had students skip pre-calc, go from advanced algebra right to BC, and they get 5s, like because they just went after it and they learned everything on their own, like the trig stuff. Yeah. Squeeze theorem. Oh, let me see. I haven't taught Calc AB in a while. I've been teaching BC, but yeah, squeeze theorem. I just think of let me see. So squeeze theorem. So here's F, and here's G, and then like here's H. So let me change colors. And this might be the last thing I say because it is late. Tomorrow is Mother's Day, and I have to stream again. So this will be the last thing I say. So here, if the limit as x approaches c, I think this is a squeeze theorem. I just know what it looks like, and that's how I remember stuff. I just see the picture. If the limit as x approaches c of g of x equals the limit as x approaches c of f of x is equal to L, and H is bounded by F and G, like this, then I believe this is squeeze theorem. The limit as x approaches c of h of x is equal to L. Okay. When I taught this like really like in depth in Calc AB, I would have a picture of like 2 like giant guys sitting on the ends of the airplane, like, or like the 3-row seats, and they're sitting on the ends, and there's like a guy being squished in the middle. So basically here, it's like, yeah, if the top function and bottom function have a limit of L, and the middle function is always between these two, then the limit of H gets squeezed to L. That's why they call it the squeeze theorem. So yeah. Yeah, I mean, if I had to make a prediction, like Calc BC, I'm gonna say it's rate in, rate out. It's gonna be polar. My guess, because they did parametric a few years in a row. Maybe it'll be like a parametric polar fusion, but I'm leaning towards polar. It'll be graph of f prime question, and then after that, I'm thinking it'll be. Wait, I could do this. Maybe yeah, differential equation with Euler's method. Maybe with integration by parts to separate variables. And then the fifth question I'm going to guess is going to be, are they going to do area volume again? Yeah, maybe they'll do like area volume with, because then that would be the AB also question. So maybe like an area volume question might be on the table here. And then 6 is obviously unit 10. That's my guess. So you'll be okay. Yeah. Oh, and happy Mother's Day to everybody's mom here too. So I'm gonna sign out though. It is pretty late, 11:30. So I will see you all. All right. If you want to stop by 3:30 p.m. 3:30 p.m. tomorrow Eastern time, I will stream, and I'll see you then. Take care and good luck. Happy studying.